all present here and those who have joined online. Dear students, researchers, and fellow friends, today is the National Science Day, and we all wish you a very happy National Science Day 2021. We celebrate National Science Day to commemorate the discovery of Raman effect by Nobel laureate Sir C.V. Raman. His discovery has made all Indians proud and is a reminder about the importance of encouraging scientific temper and humanism in our lives. The Raman effect arises when a photon is incident on a molecule and interacts with the electric dipole, setting the molecule to vibrate. The scattered photons mostly have the same energy as the incident, but the beauty lies in detecting a small fraction, 1 in 10 to the power 7 photons at frequencies slightly different from the Raman effect, from the incident light. With this, I again welcome you all to the celebrations of National Science Day this year. And in line with our previous presentations of yesterday and day before, I now invite Dr. A.K. Mishra, who is from the High Pressure and Synchrotron Radiation Physics Division of BARC. Dr. Mishra is working in BARC since 2003. After receiving his PhD from HBNI, he worked at the Geophysical Laboratory in Carnegie Institute of Washington, D.C. His contributions in the field of LaH10 superhydrides, which show room temperature superconductivity at high pressures, is acclaimed worldwide. Dr. Mishra, please deliver your lecture. Thank you.
Good morning, you all, and especially good morning to my budding students with curious minds and their dedicated teachers. So today is a very special day for all of us, because we know that a century ago, Professor Raman, he discovered the famous Raman effect with the name of the secondary radiation, and it is a very honor for all of us to remember on this particular day. Especially, I want to show you his So I want to show you his spectrograph he used for recording the Raman spectra, and which ultimately lead to discovery of this secondary radiation or discovery of Raman effect. So he used this modest spectrograph for conducting his experiments. And not only that, you will be surprised to know his passion. Actually, he joined in 1907 after completing his education, formal education, to famous, at that time, the famous service, Indian Foreign Service, to the Indian Foreign Department as a civil servant. And he lived a dual life. I'm saying dual life. You all know that photon behaves as a dual nature. Sometimes it behaves as a particle, sometimes it behaves as a wave. So he was so passionate about his work, about his job. Actually, he was passionate about science. He was passionate about optics and acoustics. So although he was an officer in Indian Foreign Service, he continued to work for almost 10 years, from 1907 to 1917, in the morning as well as in the evening, after continuing his role as a finance officer in Indian Finance Department. So he used to do experiments in the Indian Association for Cultivation of Science in the morning and in the evening. And in the end, in 1970, he decided that enough is enough, and he quit the IFD service, and he finally continued his passion for whole time. And thus he published a paper on molecular diffraction of light. So I'm saying molecular diffraction of light because those days, actually diffraction was the newly discovered phenomena. In 1902, Röntgen got the Nobel Prize for discovering X-rays. And diffraction was very new those days. In 1914, Bragg, Bragg, father and son, they discovered the diffraction through the crystals with the X-ray. And based on that, he published a paper on molecular diffraction of light. And he was so passionate about his work that in 1928, February 1928, he discovered the Raman effect and he got the Nobel Prize in 1930. So with this modest description, I will like to let you know that Raman scattering is the second most widely used technique in the whole material research arena after the X-ray diffraction. It is so impressive technique. So now let us go to our job. Like we have to assemble here to understand the synchrotron source and technology. So how the synchrotron technology helps in understanding the light. So I will let you know that the Raman used the sunlight to do his experiments. And sunlight is nothing but it gives us the visible light spectrum. So in electromagnetic spectrum, he used just the visible light portion to discover this Raman effect. And synchrotron light is such a light, is such a bright light that it gives us whole lot of spectrum in a go. So here is the outline of my presentation that I will give a little brief background and then I will talk about the technology associated with the synchrotron radiation and then I will talk a little bit about the synchrotron radiation and then I will show an example of Indus 1 and Indus 2. So here is the synchrotron storage ring with which we get the synchrotron radiation out of this. So this is going to be our final point and I will explain during this talk that how we get the synchrotron radiation from a storage ring, from an accelerator which is nothing but a circular RF accelerator. So what are the requirements for generating synchrotron radiation? So synchrotron source has the following requirements that you need light charged particle such as electron moving with almost close to the velocity of light. And you need to accelerate this particle. So finally it should gain the intermediate energy and then it should get the final energy. And then I will talk more about the journey of this electron beam in the storage ring, what are the involved things into that, what are the involved technology, and finally I will say how, I will tell you how the supply of energy is given to the electrons when they radiate the synchrotron radiation during every bend, and then finally I will delve into emission of synchrotron radiation from electron beam. So we know that materials around us are made up of atoms and molecules, and atoms are made up of nucleus and electrons surrounding it. So here is a cartoon picture of atom showing electrons around it as per the Bohr model, but actually the more scientific picture of atom is like around the nucleus, the electrons are distributed at the charge cloud. And you know the size of the nucleus is of the order of 1 Fermi and size of atom is of the order of angstrom. So the difference between the Fermi and angstrom is of the order of almost 10 to the power 5. So you can visualize this as like you all have seen a football field and you all must be seen a mustard seed. So if I consider a mustard seed as nucleus, then atom will be of the size of a football field. So to discover this nucleus, actually Rutherford, he asked Cockcroft that whether I can get an accelerated or high energy alpha particle beam. And Cockcroft Walton, he gave him the alpha particle with high energy, and thus he was able to discover the nucleus, and whole modern science evolved with the discovery of the nucleus. So that is the fundamental thing. So here you can see the difference between the Fermi and angstrom. 1 Fermi is of the order of 10 to the power minus 15 meter, and 1 angstrom is 10 to the power minus 10 meter. So now our requirement is generation of charged particle like electron. So here you can see that if I take 1 electron out of an atom, it becomes positively charged, and if you put an excess electron into an atom, it becomes a negatively charged. So how to get electron out of this atom? So metals are the best thing out of which we can get the electrons, because you can consider metal made up of ions in the sea of free electrons. I am saying free electrons because they are not as tightly bound as in a covalent solid or in an ionic solid. So these free electrons you can get very easily just by heating. So you can heat either with the Bunsen burner, and this process of getting the electron out of metals is called thermonic emission. So thermonic emission is something like here is a cartoon which shows the metal piece, and electrons are moving in this jiggling, and if you heat it, the electrons comes out of this metal very quickly. So here is a cartoon where we have a filament, tungsten filament, and if we heat it resistively, like if we join it with a battery and we flow the current into it, the electrons will be emitted all around it from the surface. And this is same phenomena as if you must be knowing that if you heat the water, the molecules from the water will, water molecules from the water liquid will come gaining the heat out of it. So similarly here also we can get the electrons out of the filament by the thermonic emission. But now here is the role of the technology. Like with the thermonic emission, what we are getting with the tungsten filament, the electrons are coming all around it. So we want more number of electrons in a particular direction, and for that people have discovered that LaB6, which is a best material, cathode material, from which you can get electrons in a very particular cone in a directional way, because you can grow a single crystal, oriented single crystal for LaB6, and whole lot of technology is involved into it. Like you can see, even for heating this LaB6 crystal, you use this carbon ferrules, and it is not just the normal electrical heating. So advantage of this LaB6 material is its thermal and chemical stability. It gives high brightness because it gives more number of electrons, and at the same time it has very narrow energy spread. So this kind of source gives you extended life and gives you a controlled source size of the electron beam. So next is this is called electron gun. So electron gun is the first point in any synchrotron radiation source from where you get the electrons. And these electrons are we get it travel inside a vacuum. Why vacuum? We need vacuum because if you get the electrons out in just that way, so you know in air, in normal air, the number of particles, number of gas particles in air in a cubic centimeter is 2.7 in 10 to the power 19, and the electron which is coming out of the electron gun, if it gets scattered with this, we will lose the electron. So the whole purpose is lost. So we have to get these electrons inside a vacuum. So vacuum is nothing but a space devoid of gases. So we have to remove the gases inside the vacuum chamber, and this is a typical cartoon which shows that how we remove the gases from a particular region. Different kind of pumps or different kind of pumping technology is used to remove the air inside a particular chamber. And in the synchrotron sources, we use ultra high vacuums. So the different level of vacuums are defined with the number of particles which are there in the region. So in ultra high vacuum, you can see it is 10 to the power minus 11 millibar, the pressure is. So it is so low pressure, and the atoms is nearly 4 in 10 to the power 5 atoms per centimeter cube in ultra high vacuum. So that is a very involved technology, vacuum technology, which is used in the synchrotron sources. So next is like we have to accelerate these electron beams. So to accelerate these electron beams, we have to now we use the electric field. So you know that in any, if we put a potential difference between two charged plates, and if we apply a voltage difference of 1 volt as shown in the cartoon here, and if one electron is traveling into this 1 volt difference, it will get energy of 1 electron volt. So now this is just the 1 electron volt DC acceleration. This is called DC. You are giving the electron a potential energy of 1 electron volt. In synchrotron accelerators or in real accelerators, we have to get this in an energy of the electrons to the giga electron volt. So giga is, you can realize from the enormosity, it is thousands of keV, not even EV. So to get that, we have to accelerate the electrons. So how to accelerate anything? What is acceleration? Acceleration is nothing but the change in velocity per unit time. So what is velocity? Velocity is a vector component, vector quantity which has speed as well as direction. So you can change the velocity either by changing the speed or by changing the direction. So like here, one cartoon shows speeding. If you all have experience of speeding the car, so if the car is speeding in then positive acceleration, and if you are slowing the car, so there can be a deceleration, or the acceleration will be in the negative direction. So you can accelerate an object either by changing its speed or by changing its direction. So similarly here I have shown by a cartoon that if you have a charged particle of charge QE, and if you apply a potential difference between two plates, so there will be an electric field from positive to negative as shown by the arrow, and as shown by the arrow. So if there is a positive charge, it will get force F equal to QE in the direction of electric field, and if you have a negative charge, it will get a field, it will get a force in the negative direction, like F equal to minus QE. So based on this principle, we have the DC accelerator, which I was saying was involved in the discovery of nucleus. So Cockcroft-Walton, he developed a circuit which can multiply the voltages, DC voltages, and that's how he accelerated the charged particles up to 3 megavolt. And another variant of this DC accelerator is Van de Graaff accelerator, where you collect the charges on a metal, dome, and this collection of charges on the metal dome creates a potential difference, and that's how you accelerate the another ion with help of this potential difference between the dome and the ground. So, but the main drawback of this DC acceleration is, like, if you want to accelerate to very high voltages the charged particle, then you have to apply very high DC voltages. And we all know that if we apply more than 30 kilovolt, like 30,000 volts per centimeter, which will give an effective electric field in that, so then the air breaks down actually. So these are the challenges involved in the DC accelerators. So to circumvent this, people use the RF linear accelerators. So where we can vary the electric field with the frequency, and you see there is a concept of linear accelerator where we can accelerate the charged particles in between these tubes, which are shown here, whose lengths get increasing as the charged particle gets more and more energy. Because as the charged particle gets more energy, its velocity increases. So we have to increase the length of the drift tube, and the charged particle gets accelerated when it is in phase with the electric field, which is varying with the frequency of radio frequency. So this radio frequency, this field is have the frequency of megahertz. So what is hertz? Hertz is nothing but 1 hertz is 1 cycle per second. Like in 1 second, the wave is doing 1 cycle as shown in the figure above. So like here, I have shown the 3 cycles, like 3 hertz in 1 second. So you visualize that how many times, when I say megahertz, so it is 10 to the power 6 hertz. So my electric field is oscillating 10 to the power 6 times in 1 second. And this is a typical cartoon which shows that this charged particle gets accelerated in between these tubes when it is in sync or when it is in sync with the electric field. So that what is the disadvantage? Why we can't accelerate too much with this Linux? The disadvantage is that the more the energy you want to give the particle, the higher the velocity it will have and the higher length of the drift you will require. So you will require a whole lot of longer and longer Linux. So to circumvent this problem, people use the other concept that is called circular accelerators. So to go to the circular accelerators, I want to introduce the concept of magnetic field. Like magnetic field helps us to bend the charged particle in a circle. So we all know that electric field is used to accelerate the charged particles, while the magnetic field is used to bend these particles in a circular path. You all must have experienced playing with these small magnets. So magnets are nothing but they have a north and south pole, and the magnetic field, the direction of magnetic field is from north to south, and the north pole they repel each other, while the north south pole they attract each other. And you can see a cartoon here which shows that all kind of different kind of geometries and different kind of structure you can make with these magnetic balls. So such is the force of the magnetic field. So using this, I want to introduce the concept of force on moving charged particles in a magnetic field. So like you all have experience of revolving a small object, circular object, tied with a rope. Like if we tie with a rope a small ball and if we rotate it, so it will have a uniform circular motion. So even in case of uniform circular motion, we know that with this thread, when the ball is tied, you have a centripetal acceleration or the tension in the string which is tying this ball, and which is the force which is making it move in a circle. So here, like at a particular time, at time t1, if its velocity is v1, and at time t2, its velocity is v2, I am saying its speed is same, but velocity is changing because the direction of the direction is changing. So here, in a different cartoon, I have shown that the change in velocity, that is v1 minus v2, that will lead to acceleration that is called centripetal acceleration or centripetal force. So acceleration is here v square by r. This can be derived. So similarly, in case of magnetic field, the role of this tension force is replaced by invisible magnetic force, and that is called the Lorentz force. And Lorentz force is given by Lorentz force on a moving charged particle is given by this law, that when you have a magnetic field and the charged particle is moving in perpendicular to this magnetic field, you get a force in the perpendicular direction as shown by this cartoon. So this Lorentz force on the charged particle is given by F equal to Q V cross B, where Q is the charge of the particle. In case of electron, Q is E minus E. So this centripetal acceleration or centripetal force, which is mv squared by r, and the Lorentz force, which is qvv. So I am saying this Lorentz force is playing an invisible force role similar to the centripetal acceleration. So if we equate these two things, we get the radius r equal to mv by qb. So this is the beautiful relation. So here it says that if you increase the energy of the particle, you have to increase the magnetic field simultaneously to keep it into the same orbit. And if you don't do that, then the charged particle will follow this rule, and if you give more and more energy to the charged particle, it will circulate or it will go into the radius with the higher and higher value. So based on this, there are two accelerators, and these are very simple concepts. Like this is a cyclotron machine where we have a magnet and of D shape, and the charged particle gets accelerated in between these, where when it comes in between these two D's, and this acceleration is across the gap. So whenever they get the energy, they start whenever they get the energy with that relation R equal to mv by qb, because energy is increasing and magnetic field is fixed here, they go into a orbit of higher and higher radius. So the drawback here is, like, if you want to higher and higher energy from the to the charged particle, you need very large magnets and very large magnetic field. So similar concept is also here in the microtron, which we are going to use, or which we are using in the synchrotron sources for initial acceleration of charged particles up to 20 MeV. So here also you can see the charged particle is accelerated from this cavity, and in a fixed magnetic field, it it follows the relation R equal to mv by qb, and after it gets accelerated up to a certain point, like 20 MeV, we get this charged particle out of this accelerator microtron. So based on this, we go to the synchrotron, which is nothing but a circular RF accelerator. So you can see here from this cartoon that the electron which we are accelerating from the microtron up to 20 mega electron volt, we put it into a booster ring to accelerate it further up to 450 mega electron volt, and then the electron from this booster ring is inserted into the storage ring through the help of kicker magnets, and in the storage ring now there are magnets, electromagnets, which we increase the magnetic field in the electromagnets as we increase the energy of the charged particles. And this is a typical cartoon which shows the synchrotron radiation coming from the bending dipole magnets, and whole lot of so this is one cartoon which shows the typical dipole magnets. So we get the synchrotron radiation emitted like a torchlight. So it is it gives us a very broad fan, and so here is a cartoon which shows how the electrons which are moving in a storage ring in a particular with a particular energy, when they are bent with a bending magnet, they gives us synchrotron radiation consisting of very broad spectrum and very bright light. And this storage ring consists of various magnets like electromagnets, dipole magnets for bending these, and then we need the quadrupole magnets to focus these electron beams to a fine size, and the RF cavity plays here the role of accelerating these charged particles, because at every dipole magnet, when they emit the synchrotron radiation, they lose their energy. So we get that energy replenished in the RF cavity. And not only we use the dipole magnets, there is a concept like we can use this series of magnets, and this series of magnets, they are called alternating magnets, and these are called insertion devices, which we put this into a linear part of the storage ring. And these are fantastic sources. They give even brighter light, even brighter radiation than the bending magnet radiation. And just for comparison, like I will show how enormous and how big this is a layout of our own synchrotron sources in RRCAT. You all might have seen in the that starting from the microtron and booster, and then we have a smaller storage ring, Indus 1, which is the 450 mega electron volt, and we have a bigger synchrotron of 2.5 GeV and 200 milliampere. So you can realize that its circumference is 172 meter. It's almost twice the size of the football field. So here I want to show you the gigantic sizes of these dipole magnets. So these are the dipole magnets which have been used in our synchrotron source in Indus 2, and these are the quadrupole magnets. So magnets in two directions, ns and ns. So basically, these quadrupole magnets focus the electron beam and make them tighter, because you will get the synchrotron radiation in a very small cone if your associated electron beam is very, very small. And these are the radio frequency cavity system which are used to accelerate the charged particle with help of the radio frequency electric field. And this I want to show the insertion devices. So this is a periodic magnetic structure what I was showing. So what this periodic magnetic structure does to electron and how this was discovered. So actually, you know, the concept looks very simple now when these are all discovered. So actually I met the person, the guy called Raman, he is still alive, who discovered this periodic structure, magnetic structure. So what he said, that they all were working with the dipole magnets, and suddenly he went on a holiday with his family, and there he saw this zigzag structure in the playground, and then it clicked to him that why we can't jiggle the electron. So he said that we got the idea from there, and he rushed back to his laboratory from his, and then they started doing research on this. So here the point is here these are not the electromagnets, these are the permanent magnets, and if you want to go to the higher and higher magnets, you have to use the superconducting magnets. So these are the technological advantages, and you know the whole length of these insertion devices is quite large, and you need to get a very uniform magnetic field into this. So out of these insertion devices, like at every bend, you get the synchrotron radiation, and depending on the undulator or whether it is wiggler, we get more coherent or more brighter light. And this is a live example of a synchrotron radiation from an undulator device. So you can change the gap between these magnets, and you can change the wavelength as well as the hardness of the X-rays. So this is a typical cartoon which shows the comparison between the radiation from the bending magnet, undulator, and wiggler. And with this, I will like to show the picture of Indus 2 just to realize how big and how much effort has gone into building this kind of mega facilities for science, where not one or two groups, whole lot of hundreds of groups are working, consisting of many, many scientists and engineers in those groups, and they have let us realize this dream of synchrotron light, which many people say that it is brighter than the billions of suns. And with this, I will talk a little bit about how the radiation is actually emitted. So we all know that the Maxwell law, that accelerating charged particle emits electromagnetic radiation, and so it is very important to understand that there is an electric field associated with every charged particle even it is in rest. So when it is in rest and when it is in moving, so when it moves with the high velocity close to the velocity of light, so due to the Lorentz contraction, the electric field swings in the perpendicular direction, and if you bend this particle, beautiful radiation is emitted, that is called the synchrotron radiation. And here this is a movie which shows that how synchrotron radiation or a charged particle emits a radiation, and this radiation is nothing but the discontinuity in the electric field lines, or disturbances in the electric field lines which propagate further as the charged particle moves or is being accelerated. And with this, I want to just emphasize that in case of synchrotron radiation, you need to accelerate these particles perpendicular to their velocity, perpendicular to their speed, and then they have to be relativistic. Then only you get the synchrotron radiation. And with this, these are the take-home messages for our curious minds, that electrons are emitted from thermonic emission and from cathode materials like LaB6, and RF linear accelerators are used to accelerate these charged particles, and the synchrotron radiation is emitted by relativistic charged particle during its acceleration. And we all must stress on the curiosity driven research, because if it would not have been there, we could not have seen the nucleus, we could not have seen the atom, we could not have seen the X-ray diffraction and the synchrotron light. And thank you all for your attention.
Thank you very much, Dr. Mishra, for this wonderful talk. May I now have a maybe now have some questions from students. Students who wish to ask a question can raise his hand in WebEx.
Mr. Jatin Sharma, you can raise your hand and ask your question.
Mr. Jatin, please switch on your video as well and unmute yourself and ask your question.
Hello, sir. My question is, can we correlate this phenomena of emitting radiation through de Broglie matter waves? And can we study the variation of emitted radiation and in variation in behavior of charged particle with the change in velocity of that particle?
Can you repeat the question, please, Mr. Jatin?
Sir, my question is, can we correlate this phenomena of emitting synchrotron radiation through a charged particle to de Broglie matter waves? And can we study the variation of the variation of radiation and variation in behavior of charged particle with the change in velocity of that particle?
Which is emitting, like we all know that any matter which is moving with some speed, it will have a wave associated with it. But here, when we are talking about the radiation, it is especially from the charged particle. So you can always study the effect of this radiation or the effect of emission of radiation on the charged particle. So all these things are done in the accelerator. Here, in case of synchrotron sources, we are using the synchrotron radiation. So we are using this principle to get the radiation out of it. But you can always study the effect of radiation, like what is happening to the charged particle. Like when it emits radiation, it loses energy, and it loses energy. So that energy is again gained here in this case with the RF cavity. But in the accelerator physics, people study the different kind of phenomena where they can collide the particles and study whole lot of scattering and physics out of that.
Ms. Jyoti Singh, you can unmute and ask your question. Kindly start your camera also. Ms. Jyoti Singh. Jyoti Singh, you are not audible. Can you unmute your mic and ask the question? You remove the earphone. We can see you trying to ask question, but you are not audible. Okay. Okay, in the meanwhile, Mr. Laksh, you can ask your question. You can unmute yourself and ask your question.
Yes, sir.
Jyoti,
Yes, sir. Sir, what are the benefits to use that zigzag means to do the zigzag path of the electrons?
Okay, so here you know that when you are in the dipole magnets, when you bend this charged particle, it gets accelerated and you get synchrotron radiation emitted out of it. So when you are making this electron to do the zigzag motion inside a periodic magnetic structure, so at every jiggling or at every turn, it emits the synchrotron radiation. So you get more and more brighter synchrotron radiation out of those insertion devices, like out of those jiggles. So with each jiggle, you get synchrotron radiation. So if it is a wiggler radiation, you get algebraic sum of this radiation, and if it is a undulator, you get a different phenomena called interference, and the synchrotron light will be even brighter than the wiggler. So you get more and more brighter light, as well as in case of undulator, you can get the monochromatic synchrotron radiation out of that.
Thank you, sir.
Raja Shanmuga Priya, you can unmute, start your camera and ask the question. Raja Shanmuga Priya. Raja Shanmuga Priya, you can unmute and ask your question.
Sir, good morning.
Yeah, you are audible.
Am
Please
I
go ahead.
audible?
Yeah, you are audible. Please go ahead.
Sir, can synchrotron radiation utilize in energy research, sir?
There is some disturbance in your audio, Ms. Shanmuga Priya. Please repeat the question.
Sir, hello.
Yeah, please repeat the question.
Can radiation energy
Breaking.
No, your voice is breaking. Yeah. Fine. Okay.
Hello.
Yeah, if there are no more questions. Yeah.
So with this,
Hello?
we thank the speaker. Is she audible? We are sorry, Priya. We are not able to hear you. So with this, we thank the speaker, Dr. Ajay Mishra, for this wonderful talk. And before going to the next speaker, who is live from the synchrotron, we'll first show you a preamble movie about the synchrotron radiation, which you all have been seeing for the last 2 days, but still it's worth showing that to get you on track. So can we have the movie, please?
The world around us is made up of matter, which is composed of atoms that cannot be seen by the human eye. To see atoms, X-rays, which have much smaller wavelengths than visible light, are needed. Other invisible radiations like ultraviolet and infrared rays are useful for studying vibrations of atoms in molecules. Laboratory-based experiments to probe atomic scale phenomena are often limited by lack of sufficiently bright and tunable sources of these radiations. The synchrotron radiation source, which is one of the marvels of modern science, produces highly intense radiation spanning the entire range of visible as well as invisible wavelengths. What is synchrotron radiation? When any charged particle like an electron is accelerated along a circular path by the action of a magnetic field, it emits what is known as dipole radiation. When the speed is increased till it is close to the speed of light, an extremely bright and well-directed radiation is emitted. The machines used to accelerate electrons to such high speeds are called synchrotrons, and the emitted light, which contains all wavelengths from infrared to X-rays, is called synchrotron radiation. In a synchrotron radiation facility, electrons emitted by an electron gun are first accelerated in a microtron or linear accelerator, after which they enter a circular accelerator called a booster synchrotron. Here, the energy of the electron is boosted up to high speeds, approaching the speed of light. Next, the electrons are injected into a storage ring made up of alternate straight sections and curved sections consisting of different types of magnet arrangements. In the storage ring, they circulate at a constant speed for several hours or even days. The emitted radiation is used for different types of experiments. over 50 light sources are in operation all over the world, including the Indian synchrotron radiation sources Indus 1 and Indus 2 at the Raja Ramanna Center for Advanced Technology at Indore. Scientists from physics group of Bhabha Atomic Research Center have set up several experimental facilities at Indus 1 and Indus 2. The fundamental parameters used to probe the physical world have given rise to various experimental techniques. For example, in photoelectron spectroscopy, X-ray photons knock out electrons from the sample. By measuring the energies of these electrons, valuable information is obtained about the energy levels of the atoms in the sample. In X-ray diffraction, incident X-rays are scattered from the sample and interfere with one another to form a diffraction pattern. By analyzing this pattern, scientists can reconstruct the structural arrangement of atoms within the material. Today, synchrotron radiation is widely used for scientific research in diverse fields. A number of groundbreaking discoveries were rendered possible only with the advent of synchrotron radiation. Several Nobel Prizes have been awarded in the area of synchrotron science and technology. Recently, the structure and interactions of proteins linked to COVID-19 have been solved using synchrotron radiation. Truly, the use of synchrotron radiation as a light source has revolutionized modern scientific research.
With this preamble movie, may I now introduce you to Dr. S.N. Jha, who is from the 32nd batch of BARC training school. He has worked towards the development of several beamlines at Indus 1 as well as Indus 2 synchrotron sources at RRCAT Indore, and currently heads the beamline development and applications section of physics group BARC stationed at RRCAT Indore. May I now request Dr. Jha to kindly start his lecture. Dr. Jha, can you hear us?
Yes, good morning, Himal. Thank you. So I just let me share the screen. Can you see the screen now? Hello?
Yes, sir, it is visible, sir.
Okay, I just go to full screen mode and let me confirm whether, yeah, is it in now full screen mode?
Yeah, we can see the screen as well as hear you. You can please go ahead.
Okay.
Thank you.
Okay, so good morning to all of you. And at the outset, let me also thank the organizer for giving me this opportunity to participate in this 3-day National Science Day celebration, and which is culminating today on 28th of February. And it was very nice introduction given by both Dr. Himal and Dr. Ajay Kumar, the effect of Raman, to recall us the great scientist contribution for our scientific achievement here. So let us start now the job. And the job is that so far we have seen the journey of the electron from, let us say, filament, lanthanum hexaboride or so, and from there how it has reached to the level of synchrotron radiation source, I mean to the storage ring, and from there the output which is coming as synchrotron radiation source, how to utilize that, because this is a unique tool, as just now you heard in very beautiful movie. So with this, now this is my the plan of the talk. So why do we need a synchrotron source? That is the first question. Yes, we all of us know now that is a brilliant source. But then the question definitely you should ask that why at all it is useful to us. Then how to use that? Once you are convinced, then how to use that? What are the ways? Then what are the beamline facilities at Indus to do the research? And then finally, I will give the glimpses of the usefulness of synchrotron source in this presentation. So the first is why you need a synchrotron source. So as you heard, it is a very high brilliance. It has a broad spectrum. It has a polarization properties and so on. So basically, there are many questions because of these unique properties. Many questions can be answered, and the questions can range based on your curiosity, like the Raman had, like the scattering of light. He had curiosity, and then he discovered this. Similarly, his questions can be also based on the societal needs of today's era. For example, you see right now, recently we heard in Uttarakhand, untimely the flood due to the breaking of the glacier. So it is a worrying point for us, and all of us has to, as a responsible citizen, we should worry. And so in that connection, like how to lead a sustainable life and how to provide a better crop with a less toxicity. So it has very important role in agriculture and also in the discovery of many new medicine. Or recently, just you saw in the video that structure of that vaccine for corona, structure of corona virus has been determined by this correlation source. So there are n number of such questions. Definitely, it will come to your mind also. And basically, the idea is at the end how to lead a better life, and how to lead a better life at no cost of our environment. So with that objective, we have to use this synchrotron for make our life better, or make or we leave the our atmosphere better for our next generation. Okay, so now we come to how to use synchrotron. And so before coming to that, I would like to just say, the conceptualize the fundamental behind the utilization of this source. As you know, like in the visible, you have a visible light, and then you use for seeing the macroscopic objects. But when you are to see this at a microscopic level, like what is happening in a, let us say, solution, or what is happening in a matter, so in that case, you have to go to X-ray. And X-ray, which is in synchrotron, then it is much more advantageous. So the first thing, like if you shine a visible light on, let us say, a window pane, so you can see some light gets transmitted or some gets scattered. Similarly, in the event of synchrotron, let us say if I shine a light on the matter, it can get absorbed and some can get transmitted. So using this phenomena, like the absorption of the material will depend on which energy of photon you are using. So based on that, we can decipher the internal structure, microscopic structure, using this X-ray absorption technique. And also we can use the for imaging purpose. Okay. So next is, if the same out of, let us say, 100 photons, some photons may get scattered at very low angle, and that is called small angle scattering. And this also can give structure at nanometer scale level. Similarly, if it is a crystal, it can give diffraction, and so you can determine the structure of a crystal structure, for example, protein. And then we can also have the possibility of reflection from the matter, and that can give rise to optical properties of the material, which is very useful for electronic industries. Similarly, this by the advent of synchrotron radiation source, the X-ray has been also used for lithography, that is micro machining purpose, a machine of the level of in the micron or nanometer scale, which can be used for example, the heart valve transplantation of the valve for the heart, artificial. Okay. And so these are the some events or some interactions which are based on scattering. Now, there are some events which are based on secondary effect. What do you mean by secondary effect? Means, let us say if you signed a photon or a synchrotron radiation, as you know, based on the Bohr atomic model, the electrons are surrounded along the nucleus in a definite energy level, and that if energy is sufficient, it can knock out the electron, and it can give either it can give a photoelectron, or it can de-excite to give rise to X-ray fluorescence. And so this can be used to fingerprint the composition, these two techniques, photoelectrons as well as the fluorescence, whereas the fluorescence gives the composition in the bulk of material, let us say in microns level, and this photoemission gives to in the nanometer level, or to give the composition of any material. So with this, now at this point, it is very pertinent to again recall our great scientist Raman. So you have already heard in the morning that there is a Raman effect. Now when you switch to X-ray, there is also called X-ray Raman scattering, and that technique also is very useful. Only thing is that this effect is, the Raman scattering so weak at X-ray, so it is very difficult to detect by normal X-ray tube, and that's why this synchrotron becomes a boon for such a low cross-section event. Low, when I say low cross-section, means let us say if you have a 10 to 28 photons, we bombard on the sample, maybe 1 or 2 event will be due to X-ray scattering. But that can be again done using a higher version of synchrotron, let us say, for example, insertion device. And you know now what is insertion device, okay? So that can be this X-ray Raman scattering is another thing to be useful by to be used as a tool for structural determination. Okay, so now you see so many techniques I have just narrated using the same X-ray photon. Now, how to utilize that? Can we do in a single setup like a laboratory-based tabletop setup? No. So we have to develop a beamline. So that's why we need to develop several beamlines based on what is your need, what is your desire for study. And then, so what is a beamline? So beamline is basically nothing, but it's an interface between, you can say, the source and you have a sample. So there is this is an interface between the source and the sample. So we can visualize. So for example, this is you can say the section of a synchrotron source, which is a dimension is of the order of football ground. So out of that, let us say small section, and then this side you have the 1 minute. So this side we have a source beyond this yellow wall, which is a shielded concrete wall, and then we receive a beam from the tangent point that is called front end. And then from the front end, the beam is transported to this optic section. So optic section is nothing but is a set of optical element like mirror or dispersing element. Okay, like in visible, you are familiar with using a prism as a dispersing element. But X-ray, we can't use that. So we use a monochromator. It is called monochromator. So this is the monochromator. These are the mirrors, because we need to you need the synchrotron in a particular shape, with a particular intensity, with a particular energy range. So all those things are done in this optic section, and then we move on to experimental station. And mind you, all this is housed in a lead wall. And why lead wall? Because it's a high radiation area, so to make a safe. So that's why another challenge is that you all work in synchrotron environment remotely. So we sit outside in this area and remotely control and manage the acquisition of data. Okay. So with this introduction, now I move to what are the facilities available in the Indus synchrotron at Raman Center for Advanced Technology Indore. And this is the you can say the schematics, which shows how many beam lines it can accommodate at Indus 2. So total 26 beam lines can be accommodated. But right now, there are 17 beam lines which are available at Indus 2, and it is working 24/7, and out of which the BRC has built 7 beam lines for several studies. And this is the list of the beam lines which are set up in Indus 1. And these beam lines are basically nothing but for spectroscopy studies of atoms and molecules and solids. And this is basically in the vacuum ultraviolet region. Because of time, I'm not going to go into detail. So, so let us now see. This is a glimpse of Indus 2, a section of Indus 2, and you can see here there are 4 beam lines housed in a lead wall. So, for example, this is a place where the imaging of the object is performed. This is a place. This is a whole hutch you can see. This is called this for microfabrication, that is lithography, and these 2 are for the local structural studies. Okay. So now I come to the last portion, which is the basically I will here illustrate the usefulness of synchronization source with using giving example on various techniques using the beamline facility at Indus 2. So before going to this example, what I would like to draw your attention that why at all we need to study structure or of atom or its electronic structure at all with of materials using X-rays. And the answer is that this is structure of the material is so important because it affects the physical properties of the material like color, hardness, density, boiling point, conductivity, etc. And for a very well-known example is, for example, this is the diamond and this is the graphite. And you know that this graphite and diamond both are made up of the same constituent element like carbon. But there is a contrasting difference between the physical properties. The diamond is colorless, whereas the graphite is black in color. Diamond is one of the hardest material, whereas graphite is very soft and is very useful as a solid lubricant. And why it is so, you can see obviously this is the structure of diamond, the microscopic structure of diamond, which you can see like a 3D image. So this is a tetragonal structure, whereas hexagonally arranged, the carbon in the graphite is hexagonally arranged and in a layered fashion. And that's why it is act as a lubricant, whereas this is one of the hardest materials. Now the story doesn't end here. It is the gross structure. I mean, you can say the snapshot of the inside of the material. But many times we come across in our day-to-day life that the properties, the physical properties of the material also is very sensitive, is very subtle to small change in the structure. And that small change we may not visualize just by looking at certain techniques like X-ray diffraction, and it may happen that it is happening at locally. And for example, in many semiconductor device or many detector, we deliberately dope in very ppm or ppb level to tune the properties. For example, the band gap, etc. Okay. So to give an analogy, I will try to pay your attention on this the picture of a classroom. And let us say if you take a snapshot, this is a snapshot of a classroom, and maybe this snapshot is same whether if you are sitting in a let us say class 9 and another class is class 10, and both snapshots look similar. I mean, so a person observing from a door will find okay, the arrangement is same. But many times you must have realized you worry about who is sitting behind me, or you are uncomfortable by the neighbors who is the next neighbors to you. And this is also true. Of course, this depends. If you are very comfortable with the friends, so you are comfortable. But if you are not happy, then you become uncomfortable. And a similar feeling you can visualize. It happens in inanimate things like in any material. So, for example, this is a manganese oxide. Now, depending upon the structure, let us say this is a structure which may be same in material, but suppose something we dope in the material, and then maybe there is slight change either in manganese oxide bond or the angle, and that can give rise to change in the physical property. So all this can be, understood. All this can be understood by several techniques, which is based on either X-ray absorption, X-ray diffraction, small angle scattering, protein crystallography for a single crystal, or using X-ray imaging. Whereas, for example, X-ray photoelectron give rise to electronic structure. So we'll see one by one to just give an example of these techniques in the next slides. So, for example, these are the two beam lines of set up on Indus 2, which is based on X-ray absorption technique. And this is for determining the local structure, or you can say your nearest neighbor structure around a particular element. And this is, for example, a picture of a monochromator, and this is a picture of the experimenter station on the. So we don't go the detail of this naming. Basically, both are for same kind of studies, but there are a variety of samples can be, studies can be done, so that if anything can be done anywhere in the world, that can be also done here. So with that idea, two beam lines in setup, and these are the view graphs of some extension station. So finally, what we gain, what you use for a photocatalyst, development of a photocatalyst or phosphor material, or for a research on battery material, or for environment, or development new material. Okay, so this is the example. Sorry, I'm sorry. 1 minute. Okay, so this is one example we have solved the myth that, Ayurvedic drugs normally in our back of the mind always is there, that it is toxic, or we are skeptical because it is not validated so far by scientific methods. And so there was one study to basically to break the myth that the Ayurvedic drug, which is called a Rasa Sindhura, which is based on mercury. So naturally, we are skeptical to know if something is having mercury, it will be poisonous. But when we did the study using X-ray absorption, and we have found that the material, it is not at all toxic, because the mercury is not present as a mercury in the zero valency state, or it is not having any organic molecules surrounding the drug. So this has been now validated scientifically using the modern synchronization science-based technique. And not only that, it is non-toxic. We have also found that the same Rasa Sindhura drug, if it is manufactured by a modern chemical route method, which is this, so it is inferior to our the method which has been described in our Ayurvedic literature. So, for example, the defects in the Rasa Sindhura, which has been developed by the traditional method, is very less than 3%, and also it doesn't contain any organic molecule layer, which is also very important to qualify any material as a drug, because it should be robust when it is delivered to the body, in the body for its action. So this is very important study which Government of India has also recently focused to validate all the Ayurvedic medicines, so it can be used as an alternative way for our health in the medical science. Okay. So next example is the study on the photocatalytic hydrogen production from water. So this is basically a catalytic reaction which is carried out using a sunlight. So we don't use any energy which is based on carbon. So, and here the objective was to find out the reason, like why it is so that some material same material having different structure gives rise to less production of hydrogen, and while some gives higher. And that we have find that this, because of this layered structure, based on the investigation, this particular structure is useful for high yield of hydrogen, which is finally going to give a remedy for alternative source of energy, which is a green energy and also a clean energy. And so this is towards our pollution-free environment, and later on it will be this technology will be developed. Next is a very important application in the lithium-ion battery studies. As you know, the government of India recently has a plan to switch over slowly from petrol-based car to battery-operated car, and in that direction, a lot of work is going on all over the world also, so that we can save our planet from the pollution. And in that direction, lithium-ion batteries are extensively used, whether it is laptop or any mobile that you know, and it may not last also. So we have to find alternative way. And also in the same lithium ion battery also used, it has not reached its full capacity. When I say full capacity, means how whether its charging time. Let us say, for example, if you are riding a car, so we'd like to have maximum number of hours for maximum hours it can retain the full charge potential, and it can recharge in a very short time. So, so this why it has not come to full capacity, because still people are working on the microscopic mechanism that how why this we have not reached to full capacity. And in that direction, we have done a real-time studies on the lithium-ion battery material, and then we have noticed that there is a distortion. There is no gross structural change, but the distortion in the structure of the material when we are switching during the discharging. So there are a lot of research going on in this direction, and we are collaborating with the various institutes here, for example, National Chemical Laboratory Pune, in this way, in this direction. Okay, now I come to the structural flow that is called protein crystallography technique, and where we use the single crystal for determination of structure. And you can see this is the view graph of the beamline, and this is the experimental station. So the sample, tiny sample, is mounted here, and then the this X-ray diffraction is collected. And this, but before coming to the synchrotron, there is a very important and very difficult, task that we have to convert the protein in a crystal, single crystal, and which is a really marathon task. And but which we have provided this facility at Indus 2. So this is the photograph of the various crystals, made in lab there. Okay, so using this crystal, now we can use this crystal for the study, and you can see here how it is done there. So we bring the crystal in the path of the beam, and then this X-ray photons gets deflected. So various waves then interfere, and because of that, then we get this pattern or diffraction pattern on the detector, and which is captured like this diffraction image. And from there, we get a electron density map. Finally, it is scattering due to electron, so we get ultimately electron density map. And from there, we get this kind of kind of protein model, and from which we finally get the structure of the protein. So this is an example of a structure of a human protein, which provides insights into the cystic kidney diseases, and these are the several protein structural has been determined, which has been deposited in the data bank, and all over the world people deposit this structure so that it will be helpful for the scientists who are in the business of the designing the new drug, because once you know, then we can design the particular, let us say, vaccine or a drug for that particular disease. Okay, so now I come to the another, sorry, 1 minute. Yeah, so, okay. So this is the another application of synchrotron, where you use the X-ray as a X-ray diffraction technique. But what here we do, we would try to see the changes in the material, structural changes, by applying external some kind of effect like temperature and pressure. So basically, this is how it is done. So we put our sample between these two diamonds, and then compress it, and then it is mounted here at the position where the beam interacts here, and then detector we record the diffraction pattern. And basically, by applying high pressure and also high temperature, we can basically mimic the condition of in the interior of the Earth. and also in the extraterrestrial planets. And this offshoot of this study also leads to the development of new materials, for example, artificial diamonds or tungsten carbide, etc. Okay, so this is another study using this beamline, and this is done in the real time. So this is similar to what I showed earlier on the lithium-ion battery, but here the objective is to find an alternative material which is not based on lithium, because so far we only use the lithium-ion battery, and there is a limited resources available on the earth, and due to growing demand, we have to find an alternative way, I mean, which is based on sodium or potassium. So in that direction, this X-ray diffraction study has been done, and to study. So basically, for example, this is let us we make a button cell and then drill a hole, and then we pass the beam, X-ray beam through this hole, and then we get the X-ray diffraction data to know about the material. Now I've come to another class of technique which is based on scattering, and many of you maybe you have visited like Uttarakhand, where in the dense jungle in the morning, if you see some kind of this image, which is called also Tyndall effect. So this is basically due to the scattering from the sunlight at a small angle, and due to the particles suspended in the air. But this is we can see with the naked eye, because this particle size is bigger in a micron. But same thing if it is in nanometer scale length, for example, 1 nanometer to 100 nanometer, we cannot see with the naked eye. So that's why we need a X-ray, and X-ray gives scattering at small angle if the material are in the size of this nanometer and 100 nanometer level. Like, for example, precipitates in a solution, or the colloids, for example, your milk is a colloidal solution, or to understand the interaction in the polymer, for example, in the tire industry, or in small granules, or the virus. So these, so basically the cluster of atoms which neither fall in the category where the normal X-ray diffraction can be used. So we use the small angle technique, and in this basically what we do. So basically this is for example is a particles. These are the particles embedded in the matrix in a material, and which has a length scale of this order. And this we can, from this technique, small angle X-ray technique, we can quantitative information we can get about the particle size, about the distribution of this particle size in the material, and about the interparticle distance, and all this, which is very helpful. For example, the milk industry, food technology industry. For example, milk. Suppose you have mixed some preservative in the milk, and sort of you want to extend the life. Now, what is the effect of that? You can see. For example, yogurt, we have mixed some in that, and then you have to see the effect. Similarly, in the industry, tire industry, or the aerosol or cement industry, this technique is very handy to for the improvement of the products. So this is a recent. This beamline has been very recently commissioned at Indus 2, and this is the one recent study, like curiosity-driven study, which finally leads to some application. So this is, for example, imagine like a lion has been captured in a small cage. So to give that analogy, so how does a water behave when it is trapped in nanometer size case? So that how the interaction changes when it is trapped in a nanometer scale. So it is a curiosity-driven studies, and so such studies will lead to finally application in day-to-day life. Okay, so now I come with another structural technique which is not based on scattering, but it is based on imaging. Now, imaging, we are very familiar from the olden days, as old as when Raman discovered the X-ray, and he showed the first X-ray videograph of his wife. And so we know that conventional X-ray is being used already in hospital, in CT scan, or in the airport. We have a security body scanner or baggage scanner, but it has some limitations. What are the limitations? It has no sensitivity to soft material tissues, or it can see that smallest particle is not more than less than 500 micron. It is time consuming also, and it also imparts a high radiation dose, and it cannot see in a real time. So to overcome such a problem, we go to synchrotron, and how it is done. So we put the object for which we want to image in between the synchrotron source and the detector, and then we rotate the object to get a 3D image. And this is the view of the beamline, and this is the view of the experimental station. And what are the features using this technique? So you can go down features up to 1 micron, and you can study in real time. Let us say I hit some structure and see what are the changes in the microscopic level happening. Then also it is sensitive to soft tissues, and it can see thin materials also. And very important it is that it also imparts very less dose. Why less dose? Because the source is so bright, even for a small time of interaction, it can give very good image that you can see later in this some example here. So, for example, this is study on the formation mechanism of the kidney stones through 3D imaging. And this the kidney stone is very common all over India, and so here the objective was to find out the nature of this stone forming. I mean, its composition wise, like what is it made of, and the structure wise, and then also to visualize, like let us say if you have data all across the country, and to make some correlation whether it is leading to some food habit or some geographical condition. So this study has been done in collaboration with the doctors, and this is, for example of hip-bound human-borne disease, which has been done with a high-resolution X-ray imaging, and this is an example on aircraft composites which have been imaged to see any defects in the material, which has found application in the aerospace engineering. Now I come to the technique. I'm coming to now the last slide. So this is a technique for finding the electron structure in the material, and which is based on, you have seen this photoelectron spectroscopy in the movie before this talk. So basically, when you shine a photon, then the electrons is ejected, and if you measure this electron energy property, electron energy, we can say from what kind of element it has come. So that's why it gives rise to type of element present. Also, it is in which form. It is having which valency. So basically, the photoelectron spectroscopy gives you elemental composition in the surface or in the bulk material. It gives you also the empirical formula, like whether it is a copper sulfate, when it says USO4, so that you can find out the formula of an unknown molecule. And also it gives a chemical state. For example, I showed you the mercury sulfide. Now this can also give the surface, if I use this technique, you can also get this how the mercury in 0 state or in +2 state. So basically this is the energy level diagram just to illustrate. We can, and not only that, this also we can use this technique, whatever you have studied the Bohr's model in your 9th or 10th class, you can validate this the quantification of energy, like energy level, like we will get only electrons of this energy, either 2p level or 2s level or 1s level, will not get in between electron. So this is another, this is the, you can experimentally observe the Bohr's model, what we have studied in the classroom. And these are the monochromator, which has been developed indigenously in ERC. So with this, I come to the end of the presentation. And this is just a view graph of the footprints of the users all over the country using this beamline facility. So with this, I now must thank you all for listening this presentation. And now I am very happy if students ask some questions, and I'll be happy to answer them. Thank you.
Thank you, Dr. Jha, for this wonderful talk. So students, you see the various kinds of applications which includes imaging, diffraction, material science, and biology. So we request you to please ask your questions by raising your hand in WebEx. Whoever is raising his hand should unmute his mic before asking the question and start his video as well. Dr. Jha, you can stop sharing your screen.
Okay, okay,
Miss
okay.
Miss
Yes,
Ayushi
sir.
Somkuar.
How to do
Miss
that?
Ayushi
Just a minute.
Somkuar, you can unmute your mic and then start your camera and ask your question. Miss Ayushi Somkuar.
Yes. Good morning, sir. So we can mimic the interior of Earth. So can we recreate the fossil fuels using that?
For what?
Can you please repeat, Ayushi?
We can mimic the interior of
How to
Earth.
share screen?
It's echoing.
Ayushi, can you please repeat the question?
Closer to the mic and repeat your question.
Ayushi, can you please repeat the question?
We can mimic the interior of the Earth. So can we recreate the fossil fuels?
No, the recreation of, we can study the fossil fuel. That we can do. See, we can recreate the condition. So as I told you, like in the earth crust, we know there is a diamond available. So same condition if you recreate, you can make a artificial diamond. Okay. The recreation of fossil is different phenomenon.
Mr. Shreyas Karanjikar, you can unmute yourself, start your camera and ask the question. Mr. Shreyas Karanjikar.
Hello.
Shreyash? Yeah, please go ahead.
Sir, I have a question. Sir, just like synchrotron is a particle accelerator which in which we accelerate electrons, okay?
Yes.
So just like it has various applications in other than physics field, so do particle accelerators like Large Hadron Collider have similar applications because it is LSC is way bigger than synchrotron. So does it have similar kind of applications?
No, no, it doesn't have similar kind of acceleration because there we use a proton, and for synchrotron we need a light charge particle. Okay, so their objective is one point goal is there to understand the fundamental particle, like the whole universe, whole world is working on that. So there you cannot produce because it is a proton. I mean, the efficiency will be very poor. So that's why it is objective is not there. Okay.
So it is just for research.
Yeah, yeah. It is for research for understanding the fundamental particles structure.
Oh, yes. Okay, thanks, sir.
Ms. Aisha Bhagwan, you can unmute your mic, start your camera and ask your question. Ms. Aisha Bhagwan.
Sir, good morning.
Yeah, good. Yeah.
Sir, there are side effects of synchrotron radiation or no?
No, there is no side effect. There is all positive effect, no side effect.
Okay,
See, whatever radiation you saw, because we understand radiation very well, so there is a remedy. See, there is a lion in the jungle, okay, but that doesn't mean we should not go to jungle. We have to handle, you know how to handle the lion in the jungle, okay. So we know to seal, how to seal the radiation.
Would have enjoyed. One more question is there.
Students, by now you would have understand that this synchrotron accelerator is a wonder machine. I think a lot of you might be having questions in your mind. You can come forward and ask them. This is a very wonderful opportunity to interact with experts in the field who have built and are operating and doing research on synchrotron radiation beam lines. You can come forward with your questions. Miss Anjana, you can unmute and ask your question.
Hello, sir.
Yes.
Sir, I have a question. Is the temperature of synchrotron radiation yesterday we came to know that it can drill holes, like it has a very high temperature. So is
Yes.
its temperature comparable to that of the sun?
No, no, it's not comparable with that. It is
Acha.
just sufficient to melt or drill, but not, you cannot create that condition. It is not possible.
Okay.
Mr. Jashan Mehta, you may unmute your mic and ask your question.
Good morning,
Mr.
sir.
Jashan.
My question was,
Mhm.
sir, can a synchrotron be used to recreate events just after the Big Bang?
Can you repeat the question?
Sir, can a synchrotron be used to recreate events just after the Big Bang?
Not really. Not really. So that means you need that is kind of thing which can be thought of at the that hadron collider machine. That kind of mimicking can be done there, not with synchrotron. But it's a good imaginative question. Thank you.
Arzu Dagar, you may unmute your mic and ask your question. Arzu.
Arzu, please switch on your video as well. Unmute yourself.
Arzu Dagar, you may unmute. Mr. Vishwajit Kumar, you may unmute your mic and ask your question. Vishwajit. Okay,
Good
if he's
morning,
not
sir.
able to, yeah.
Okay.
Sir, to ask that that Latent had a Large Hadron Collider (LHC), I have read it somewhere that it leads to the formation of black hole, minute black hole. So, can synchrotron also cause black holes, sir?
No, 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 no. But I think I'm not also expert on that. But definitely it cannot be created here. Okay.
Mr. Adarsh George. Mr. Adarsh George, please unmute and ask your question.
Hello.
Yes.
Good morning, sir. Sir, I'd like to ask, like when does one use platinum coated reflecting mirrors, and when crystal monochromators are used in beamlines of synchrotron?
Yeah, very good question. That means we have very seriously seen the movie and listened the lecture. Okay, so platinum and platinum mirror is used because of you have to reflect X-ray. Like unlike your visible mirror, we don't use platinum. Okay, and you use very small, even a small mirror, you can see the face. And so because platinum is very having high density. Okay, so because of high density, you can have a reflectivity will be very high. Okay, and with that also gives also freedom. We can shine the X-ray at slightly larger angle. Larger means less than 1 degree. Here for X-ray, larger angle means in less than few degree. Okay, and the second question is yours about monochromator, right? Yeah, so monochromator you use to basically like just like prism, we use to disperse the visible rays. Here we use monochromator, which is based on silicon crystal. And instead of one crystal, we use two crystals. That means we allowed to have two bounces from the crystal to get a best quality of the, I mean to get the narrow bandwidth, narrow width in the narrow spread in the energy. Okay, for example, let us say I have a 10 keV photon. Now I want the precision 10 keV plus minus, let us say 0.1 eV. So that order. Okay. Is it clear now?
Mr. Jatin Sharma. Mr. Jatin, you may unmute your mic and ask your question. Mr. Jatin.
Yes.
So my question is, in a synchrotron, we accelerate charge particle to very high velocities. So their mass are also changes. So
Yes.
can we get the gravitational waves from the change in mass?
No, 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 I don't, we cannot detect gravitational wave in a normal environment. For that, we need a very special technology, and India is participating in that movement also for the gravitational wave. And Rajaramana Center for Advanced Technology, in fact, the whole Department of Atomic Energy involved in that to set up a large facility. It ranges in kilometers because it is such a subtle effect. It needs a very high precision, high technology involvement, and the DAE is involved as a partner country in that project. Government of India has already funded for that project.
Okay, sir.
Okay.
Mr. Laksh, I think you have another question. You can quickly come forward with it. You
Yes,
unmute
sir.
your mic and ask.
Sir, when the electron gun shoot the electron and then it goes in the booster and their speed is increased, and afterward means in movie it's shown that afterward it goes to Indus 2 and again speed is decreased and it moves in a constant speed for hours and hours and it gives synchrotron radiation. So why they use booster? Because again the speed is decreases only, no?
No, so booster, as you name itself says, it boosts the energy. Booster is purpose is energy is boosted. Now for synchrotron, we need certain energy to get energy in the region of X-ray. Now booster, if you booster, you can also tap the synchrotron radiation, but that is not of your interest. Our interest in X-ray region. Let us say 10 keV and beyond, or 5 keV and beyond. And for that, we need high energy. For example, Indus 2 is at 2.5 giga electron volt. So from booster, we bring to that synchrotron, and there we accelerate by a RF energy booster to get it 2.5, and then we store it for hours and hours in the chamber, which is at a vacuum, high level of vacuum, and to get the beam.
Okay, sir. Okay, thank you, sir. Thank you.
So it is very heartening to note that all students have keenly watched the videos and are very like closely what you can say are attentive to these lectures. It is very evident from their questions. Really kudos to the student community out there online. Yeah.
Yeah, so they have actually appreciated the technologies also. The questions ranging from various different kinds of accelerators to the LIGO project as well. So you understand that every accelerator, every kind of this big machine
Mr.
requires so
Himal,
much effort.
there is a question from one Mr. Bhushan Kumar. Bhushan Kumar, you can unmute your mic and ask your question.
Bhushan, would you please also switch on your video?
Am I audible?
Yes.
Sir, is there any drawback of synchrotron?
Drawback of synchrotron? Why
Yes, sir.
it has come to your mind? There is no drawback at all, because it gives more answers than posing a question. The only posing is that you have certain radiation, okay? I mean hazards that we described, but that can be tackled, as I mentioned. So you remove from your mind, there is no any side effect or anything from synchrotron. It is a win-win situation. Why win-win? Because we not only helps in science, also it helps in developing the offshoot products. Like we have developed many that development of pumps and many local. I mean, industry has come by this setting of the Indus facility at Indore. So there is no harm at all with this synchrotron setting up. In fact, all over the world, people are having more and more synchrotron. So that shows that there is no harm in that. More than 60 synchrotron sources are available, and people are going to upgrade this because of they have a photon crunch that I mentioned. For example, X-ray Raman scattering. So we need a further brighter source. Okay, and India also is planning in that direction. Maybe by the time you finish your postgraduate, you will have the Indus of the higher version, maybe Indus 3. So I wish that we come, you study later and take science as your career. Thank you.
One last question, Mr. Sanket Jagdale. Mr. Sanket Jagdale, you can put on your mic
Which
and ask your
monochromators?
question.
Which monochromators are used with synchrotron radiation?
Which monochromator? It is called a double crystal monochromator, which is generally used for all the hard X-ray, I mean the X-ray based beam lines. Okay, and it is used as a silicon 111. If you are familiar with this terminology, so silicon 111 plane is used to diffract the X-ray to get a based on the Bragg law. So based on n lambda 2d sin theta, we disperse the from the continuum X-ray to get a single wavelength. And instead of one crystal, if I use two crystals, we further narrow down the energy width, as I mentioned in my some of the last question somebody asked. So, if you want to go for further high resolution, then we use like silicon 311, okay, such kind of crystal. So it is called silicon 3111 crystal monochromator. Instead of silicon 111, we use 3111. Okay.
So thank you, students. So you see that the development of such large facilities and novel technologies also leads to several spin-offs and industrial applications. And BRC is in fact actively indulged in several technological aspects in various areas of science and engineering. So before moving on to the next aspect of synchrotron radiation in extraterrestrial space, we show you a few BARC technologies, and which will also give you a sort of break from the theme subject for another 10 minutes or 15 minutes, after which we'll be going to the astrophysical aspects. And I also thank Dr. S.N. Jha from Indore for such a wonderful and nice lecture and crisp and to the point answers to several questions. Thank you, Dr. Jha, for joining us. Thank you. Can we now have BARC technologies, a few of them, please?
Water is a precious natural resource requiring efficient management and conservation. BARC has contributed significantly to the management and conservation of water resources by using the technique called isotope hydrology. Isotopes are variants of the same element differing in atomic weights due to variation in the number of neutrons in the nucleus. In isotope hydrology, the ratios of isotopes of elements are measured, and this information is used to devise strategies for water conservation in the affected areas. The hydrological investigation commences with the collection of water samples from the water sources for the measurement of isotopic ratios. Using isotope hydrology, the catchment areas of various drying springs in mountainous regions are identified. Construction of suitable artificial structures is then carried out to increase the water flow. Confirming the presence of ancient buried water channels, known as paleochannels, detected by satellite thermal imaging is another useful application. These channels can be revived and used for transporting water from the Himalayan heights to the distant plains. Several groundwater resources in India are affected by increasing salinity and contamination by fluoride, nitrate, arsenic, etc. Measures can be evolved. The involvement of local bodies and communities is actively encouraged to speed up the implementation of measures for the conservation of water resources. Isotope hydrology has benefited large sections of population and can be regarded as one of the important societal benefits accruing from the research activities of BARC. Loses about 20% of the food during storage and transit. Insects and microorganisms are primarily responsible for spoilage of food. Warm and humid climate in India is especially favorable to their growth. Radiation processing of food by gamma radiation is an internationally accepted, safe and cost-effective solution to preserve food products over long durations. More than 15 facilities have been established across the country to process food products using gamma ray based technology. Low doses of radiation delay ripening of mangoes, prevent the sprouting of onions and potatoes, and disinfect cereals and pulses. Slightly higher doses can prevent spoilage in spices, herbs, and minimally processed vegetables. Radiation processing techniques have also been developed to extend the shelf life of baked food, pulao, puran poli, meat, fish products, and health drinks by several months. User-friendly technologies for the preservation of delicate fruits like lychee, as well as processed food, have also been developed and deployed. Eco-friendly packaging developed by BARC are also in extensive use in the food industry. A plant has been established for medium-dose radiation processing of spices in Vashi, Navi Mumbai. A low-dose radiation processing plant, Krushak, has been established at Lasalgaon near Nasik for processing of agro-products. Radiation processing of Indian mangoes at Krushak has enabled the export of mangoes to USA. The technology is now also being extended to other fruits like pomegranates. This program remains one of the proud contributions of BARC to the food security agenda of the nation.
India is the second largest population in the world. The cities are crowded. Large quantities of wastewater is generated by human activities. Normally, wastewater is delivered to river or seawater. It contains pathogens and bacteria. The safe disposal of domestic and industrial sewage is a matter of great concern. The presence of pathogens and toxins in the sewage pose a threat to health and environment. Cities like Ahmedabad treat their sewage at sewage treatment plants. The solid sludge is generated at the end of treatment cycle. In our country, millions of tons of highly infectious sewage sludge is produced every day. What to do with it? World over, the sludge is used after proper treatment in agriculture applications, landfill and power generations. Besides pathogens, sludge contains valuable micro and macronutrients. Radiation technology, which uses high-energy gamma radiation, is known to kill pathogens and degrade chemical contaminants. This indigenous technology is widely used world over for sterilization of medical products and food preservation. Infectious sludge can be hygienized in a similar manner to make it safer and useful. Process, dry sludge containing 25 to 30% moisture is picked up by dumpers from STP drying beds, which is brought to sludge irradiation facility. The sludge is crushed using crushers and transported to carrier boxes through a transfer conveyor. In a fully automated process, the filled boxes are loaded to moving overhead plant conveyor. The conveyor carries the boxes to irradiation cell, where the sludge gets irradiated to radiation dose of 10 kg, which is sufficient to kill pathogens and partially degraded chemical contaminants. indigenized sludge is moved to liquid biofertilizer station, where it is sprayed with liquid biofertilizer containing consortium of useful bacteria which mobilize nitrogen, phosphorus and potassium in the soil for use by plants. This enrichment makes the treated sludge as a value-added product for agriculture applications. Considering millions of tons of sludges generated in our country every day, the use of radiation technology will recycle this infectious waste material to manure and derive economic benefits and protect health and environment for a cleaner and healthier India.
With this few overview of some facilities, we can now move on to the second aspect of synchrotron radiation research, which leads us to the extraterrestrial space, to the mysterious world. So you had been hearing about this topic since the last 2 days. On first day, Dr. Dipankar Bhattacharya introduced you to the subject and nicely described all the physical phenomena over there. Yesterday, Dr. Sundar described a lot of nice things about the synchrotron radiation in universe. And today, in line with this program, we have Dr. Subir Bhattacharya, who is from the Astrophysics Division of Bhabha Atomic Research Center, which is engaged in setting up various high energy telescopes at Mount Abu and at Hanle, Ladakh, which is called MACE. And he also collaborates with various astronomy related institutes in India, including TIFR and Ayuka and Manipal University, I guess. So I request Dr. Subir Bhattacharya to kindly deliver his lecture. So this lecture is also about the opportunity in the area of observational astronomy in India. As you can see the title. So can we link this, share this?
Synchrotron radiation is omnipresent in the universe. It is produced when highly energetic charged particles such as electrons and protons spiral around magnetic field lines at a constant speed, and it spans over the entire electromagnetic spectrum ranging from radio waves to gamma rays. Energetic particles are produced in different corners of the universe by some processes still unknown to mankind. When energetic particles enter the magnetic field of Earth, they produce geosynchrotron radiation in radio band. Up in the sky, heavenly objects emit much of their energy through synchrotron radiation. In our Milky Way galaxy, rotating neutron stars with very strong surface magnetic field are born after supernova explosion. They produce pulses of synchrotron radiation due to the spiraling electrons in their surface magnetic field. Beyond the Milky Way galaxy, gigantic jets powered by supermassive black holes at the center of different galaxies show their presence through synchrotron radiation. Atomic Research Center has set up one of the largest gamma-ray telescopes, MACE, at highest altitude in Hanle, Ladakh, to probe the high-energy processes related to synchrotron radiation from various sources in the universe.
So with this nice movie preamble, I am inviting Dr. Subir Bhattacharya, whom I have already introduced you before the playing of this movie. And this will be a short presentation, after which we also have Dr. Nilay Bhatt and Dr. Sundar from Astrophysics Division of Bhabha Atomic Research Center. This session is basically focuses on the observational astronomy in India, the present and future facilities and the kind of careers that you people can think of in this fascinating field. So after this talk, please prepare a few questions and we are ready here to answer those questions. I invite Dr. Subir Bhattacharya to deliver his talk.
Okay, thank you, Dr. Bhatt, for your kind introduction. Well, I'm going to talk on this observational astronomy in India, present and future facilities. In this presentation, I'm going to tell you what are the observatories presently working in India, presently operational, and they are in different wavelength ranges, starting from radio to gamma ray. So it will be radio, optical, X-ray, gamma ray. So I have essentially divided them, these observatories, according to their wavelength ranges. Now, there is a basic question that why we need so many observatories in different wavelength range. So before going to tell you about the observatories and what are they doing, let me convince you that we really need observations in different wavelength ranges and to have some sensible science. Well, so this is sun. Sun in different wavelength range. The image in infrared, optical, ultraviolet, and X-ray. Now what we see, if we see the optical image of the sun, it looks very quiet, very decent object. But when you see the same object in IR, UV, and X-ray, we see that lots of activities are going on. It is not a quiet stuff. And if we wouldn't have observed this source in all these wavelength bands, it was not possible for us to know about such activities. So now the question comes, what are the physical origin of those activities? And from that point, the physics of the source starts. Okay, so in the next slide, this is Crab Nebula in different wave bands. It is in radio, infrared, optical, and X-ray images of the same source. So what we see that the source is very different they appears to be very different in different energy bands. So the true picture of Crab Nebula is this. Had we observed it in only one energy band, we would have missed many things, and our understanding about the source, about the nebula, will be incomplete. So if we want to understand Crab Nebula and its activities, its behavior, this is the image, what we should try to explain, the second image, what we should try to explain. So if we understand this behavior, this image, then we can really understand the behavior of the nebula. Next comes a radio galaxy M87. Now what we see here, the images in three different bands again. This is in radio, this is in optical by Hubble Space Telescope. This is actually the real image of Hubble Space Telescope in the sky when in 2009 the service mission went there to do some servicing work of the telescope. This image was taken at that time. And here it is Chandra X-ray Observatory. So it is in X-ray, it is from 0.2 to 10 keV X-ray image. Now again we see that this is the jet of M87 which is coming out of the center of that galaxy with the speed, almost the speed of light. This jet shows different structures in different energy bands. So if we want to understand the jet dynamics, why and how it is created, how it is radiating energy, photons, so we should have a complete view in different wavelength range, then only we can have a actual view of this source. So it is very important to observe a source in different wavelength ranges. So I hope that I am able to convince you. And that's why we need different observatories to do astrophysics. Now, these observatories cannot be built by a single institute or single group. So different institutes, they construct their observatories for their in different wavelength ranges. So let me start with this. So the last three slides, the basic takeaway is that multi-wavelength view is essential to have a more complete picture of the cosmos. So now I go to the observatories in India. The first is GMRT, Giant Meter Wave Radio Telescope, Narangaon, Maharashtra. It is near Pune. This telescope, it has 30 fully steerable parabolic dishes, and the aperture of each dish is 45 meters. And these 30 dishes are spreaded over 25-kilometer stretch around that Narangaon area. And the main science goal of this, this telescope is to study the galaxy formation. This is that epoch of galaxy formation. This gives a lot of information about the origin of universe and the structure formation, how this galaxy, this universe is having this kind of structure, how this galaxy clusters, they are formed and when they were formed. Another important aspect is that pulsars and neutrons are studied by this radio telescope. And finally, third is that galactic and extragalactic different radio sources, such as one of such source I showed you, that M87, the radio galaxy. Such kind of radio galaxies can be studied with this source, with this telescope. And anyone from any institute can write proposal for the observation and carry out their observations. Next, the optical telescopes. India has many optical telescopes at this moment. The biggest one is the International Liquid Mirror Telescope at Devasthal, Uttarakhand. It's a 4-meter telescope. It is a mirror it is a rotating liquid. The liquid is mercury. And then another telescope which is 3.6 meter reflecting telescope. These two telescopes are run by ARIS, that is Aryabhatta Center for, it is Institute for Observational Science, I think. Then the Himalayan Chandra Telescope, which is a 2-meter size telescope. Here 2 meter, 4 meter, this is the size of the mirror. At Ladakh, run by Indian Institute of Astrophysics. There is another optical telescope in Ladakh, that is Growth India Telescope. This is the first robotic telescope of the country, run by IIT Bombay. And this does not require any manual intervention for the observations. And the Guru Shikhar Observatory is a 1-meter telescope at Mount Abu, Rajasthan, run by PRL, and Venuappu telescope, 2.3-meter telescope at Kavalur, Tamil Nadu. It is run by Indian Institute of Astrophysics. Now, all these telescopes, they are primarily used to study stars, stellar variability, binary systems, then the star formation and stellar evolution, interstellar medium and dust, formation and evolution of galaxies, and of course the AGN and their related phenomena. So with this kind of telescopes, you can do this kind of study, in some cases with long exposures, very well. Then comes the X-ray telescope, AstroSat. This was launched by ISRO in 2015. This covers an energy range from 3 kV to 100 kV. It has many different detectors. There is a large area proportional, xenon proportional counter detector is there. There are 3 in number, 3 detectors, proportional counters. There is one CZT based detector which operates in the energy range of 10 to 250 kV. There is one soft X-ray telescope which operates in 0.2 to 8 kV. It has the imaging capability as well as the capability to do line spectroscopy. Apart from these 3 X-ray telescopes, there is one UV telescope, which is an imaging telescope, and one scanning sky monitor, which keeps on looking at the sky continuously in search of some exotic phenomena which is taking place in any source. So this telescope, it is very good to study the systems, black hole systems, neutron star binaries, where a lot of hard X-rays are generated through accretion process, and it is very good to study transients. Then we go into the gamma ray domain. In gamma ray, Bhabha Atomic Research Center runs the telescope TACTIC, TeV atmospheric Cherenkov telescope with imaging camera at Mount Abu, Rajasthan. This is in fact the first imaging telescope in Asia. And it consists of 4 elements that you can see in this picture. And each element it has a dish of 4-meter diameter. In the center of the imaging camera, at the focal plane, in this imaging camera, it has 349 photomultiplier tubes, and it operates in the energy range of 800 GeV to 20 TeV, and it is at an altitude of 1.5 kilometer. Now, what is important here is that this telescope does not detect the gamma rays directly. There is some indirect way to study this. It actually detects Cherenkov photons, which are generated in the air shower. I am not going into those details here. The basic science goal for this telescope is to detection of gamma rays from galactic and extragalactic sources and search for the origin of cosmic rays through the detection of gamma rays. And one should note that this origin of gamma rays, this is a century-old problem. Cosmic rays were first, officially discovered in 1912. Till now, there is no understanding that how and from where they are coming. This is a Hagar telescope. This is an array. It works in the wavefront sampling technique. This telescope is run by TIFR. It operates in the energy range above 1 TeV. Now, these 2 telescopes, that is TACTIC and Hagar, these are a bit old telescopes. Now, BRC has come up with a new telescope imaging, again, it's an imaging telescope. It has a diameter of the basket is 21 meter, and the imaging camera consists of 1088 photomultipliers. The number of mirror panels on this basket is 1424, and it operates in the energy range 20 GeV to 10 TeV at an altitude of 4.3 kilometer. It is at a place, Hanle at Ladakh. Now, the science goals for this telescope is the understanding the gamma ray emission process in pulsars, supernova remnants, active galactic nuclei. Again, the study of this origin of cosmic ray, and the most important is the detection of gamma rays from dark matter. Now, I come to the upcoming telescopes. Well, the situation has changed a bit after the detection of gravitational wave by LIGO that you people are aware of, and the detection of astrophysical neutrinos by ice cube detector. One thing is now very clear, that this gravitational wave detection and understanding the phenomena, it requires the simultaneous detection of neutrinos as well as electromagnetic radiation from such sources. So this multi-wavelength approach of astronomy has changed to multi-messenger approach in the astronomy. So in this condition, with this perspective, we now require large telescopes, and those large telescopes cannot be made by a single country or a single group. So big collaborations have come up. So, and along with those big collaborations, there are our homegrown projects are also there in India. So many new international collaborations are initiated, and India is part of such collaborations. The first is in radio astronomy, the square kilometer array. This is an array of, this will be an array of several telescopes, hundreds of dishes and thousands of low frequency aperture telescope. The plan of the array is like this, this star kind of this feature, and this will actually cover the 2 continents. It is not at one location, and each dot consists of several, cluster of mini telescopes like this. Here, this is of course an artist's impression. It will be like this. You have low frequency antenna, and as well as those dishes which are spreaded over large region. And India is a part of this square kilometer array collaboration. In optical, this 30-meter telescope is coming up. This is possibly, this will come up in Hawaii, but there is some confusion because of the local protests and all by the tribals there. So there is a chance that this telescope will be placed in La Palma, Spain. So India is again the part of this large collaboration. This is very good for cosmological study, the study of the star and galaxy formation, large-scale structures, and the black hole environments. This is very important. This is a very important telescope in optical region. Here it is one X-ray mission, Daksha. This is a fully Indian satellite. This is by IIT Bombay again. Actually, there will be 2 satellites which will be orbiting around the Earth, one in clockwise direction, another is anti-clockwise direction. And this will cover the whole sky and continuously watch the sky if anything is happening anywhere in any corner of the universe. The most advantageous thing is that using both the satellites, we will get the 100% sky coverage. And it is expected that gravitational wave events can be observed with this telescope simultaneously in the X-ray domain. Here is another experiment. This is X-ray polarimeter experiment. This is by Raman Research Institute. This will be very soon. It will be flown by ISRO, and this instrument will be placed in the orbit. This measures the polarization of high energy X-ray radiation, and the main objective for this to understand and map the magnetic field distribution in different astrophysical sources, and this will give us the idea about the geometric anisotropies in the source as well as the cosmic accelerators, the idea of the behavior of the cosmic accelerators. Then in gamma ray astronomy, this Cherenkov telescope array, this is a big collaborative effort. There will be two arrays, one in the northern hemisphere. There is a northern array in Spain, and there will be another in southern hemisphere, that is a southern array in Chile. This array, this will consist of three types of telescopes. One is a 23-meter diameter large size telescope, and 12-meter diameter medium size telescope, and small size 4-meter diameter small size telescope. It will cover an energy range from 20 GeV to 300 TeV. And here I have written the number of telescopes which will be used for large size. In each array, 4 telescopes will be used, 4 in northern, 4 in southern array. For 12-meter diameter, 15 telescopes in the northern array and 25 telescopes in the southern array. And in case of small size telescopes, no small size telescope will be used in northern array, but southern array will use 70 such telescopes. This is the base array which will be functional possibly by 2025. But over and above, more telescopes will be added slowly. So the main science program is the dark matter study, galactic center survey, galactic plane survey, because we expect a lot of high energy sources, and particularly the cosmic accelerators are actually confined there. So these cosmic pivotrons, that is which can accelerate particles up to 10 to the 15 electron volt, which is the main constituent of this galactic cosmic rays, as well as this cluster of galaxies and active galactic nuclei. So many activities are going on, and we are a part of that. In fact, the CTA consortium, there are 31 countries and total 2002 institutes and 1,466 members. Here you can see all these countries which are shown in deep blue. They are the part of this consortium. Well, India is invited to join, but we have still not formally joined there. Okay, so I'll end here. So lots of opportunities are awaiting for you. Come, join, and expand your imagination as much as possible. Thank you.
So, thank you very much, Dr. Bhattacharya, for this insightful talk on the prospects in the field of astrophysics. May I now open the session for a few questions. Students who wish to answer the questions can raise their hand in WebEx.
You can. Miss Priya, the panel will be answering your questions. Dr. Subir Bhattacharya, Dr. Nilay Bhatt, and Dr. Sundar Sahayanathan. A panel has been is now ready to answer your questions. Ms. Priya, you can unmute and ask your question.
Am I audible?
Yeah.
Do you have any advice for someone who is trying to get into the field of observational astronomy?
Can you repeat your question?
Do you have any advice for someone who is trying to get into the field of observational astronomy?
Well, so advice means first thing is that you should be a graduate in physics, and that is the first requirement what you should have. Apart from that, you should be very fond of doing experiments and frame experiments. So, so you should learn a lot of experimental techniques, and the regular experimental, I mean, in your curriculum, whatever experiments you have and all, in your laboratory sessions, that you should learn properly, because from that point you can start actually developing your skills. And then you should appear for different interviews and all, so that you can join any of these research programs. So, and finally pursue your career in observational astronomy. There are plenty of scopes here in India.
Yeah. So the basic idea is clear your fundamental concepts very nicely.
Yeah, Miss Evelyn Kaur. Miss Evelyn Kaur, you can unmute and ask your question.
Hello, sir. Am I audible?
Yes, you are audible.
So my question is like there are many stars far away from us, very long distance, like exoplanets and many stars. Then how do we find out what is the matter inside them? How do we find out?
Okay. See, you have. Let us come to the terrestrial. So you are having a different. Suppose you are lighting a gas stove. You are ironing a dress. Okay. So you are having. You are burning. You are heating up an iron rod. So if you see, as you heat up, they all have a certain characteristics. When you heat up an iron rod, it becomes red hot. When you light a gas stove, it burns in blue. When you heat up an iron, it becomes warm. There's an infrared. So this is first thing is what happened. The color of the light, what you are going to receive, depends upon two things. One is what is the composition that gives rise to different light colors. Other thing is how hot the matter is. That's what we are doing. When we look at the star, we don't have it. We don't have the material in our hand. What we see is we see the color, and we try to see what are the line emissions there, and what is the wavelength the whole star is emitting. So then we can find out from that radiation, we can find out what are the constitutions of the matter in the star and what is the temperature. Well, this is mostly for nearby stars. I can tell you the question. Your question is very important. This is one of the most challenging thing in astrophysics, because the whole universe communicates with you in terms of radiation. Of course, now we have gravitational wave and other neutrino and all. Initially, the whole universe is communicating to us in the form of light. So you have to decipher what is that made up of from the light you are receiving. Okay, so the only way we can do is we have to compare that light with our terrestrial light, and you see, okay, they both match. That means that star is made up of this material, or the galaxy. This is what is happening in the galaxy. This all the things you have to. It's like a puzzle. The universe gives us a puzzle. You have to solve from the puzzle.
But sir, is it possible that there is some matter which is hiding behind our eyes, that is not giving any radiation, or it is not visible? So there is some matter in our sun also that we have not yet discovered.
Correct. See, the point is, if it is not radiating, it's not possible for us to see. So we are blind to it. That's what in the talk yesterday I said, if you are confined only to the visible light, suppose we are believing only our eyes, our whole universe, you would have thought the universe is emitting from violet to red. Nothing exists beyond that. The moment our technology and the smart humans come, they try to venture into unknown areas. Then we come into the picture, oh yes, the universe is hiding something from us. The whole thing in the astronomy is to find out what is hidden from us, what the universe is hiding from us.
Okay, good.
Yeah,
So
there
the
is
whole
there is a
story comes
Sir,
from
can I
planetary
ask one
interiors.
more question?
yes, beta.
Yes,
Yes,
go ahead, go ahead.
you can ask.
Yes, sir. This like we are seeing stars from many light years away from us, like our sun gives us light. Thus, the light is isotropic, right? Yes, the light is isotropic. That radiation and light, it is isotropic, which the stars give. So, but there is one radiation, this synchrotron radiation. It goes in a directed path. It is very straight. So we see stars. It is due to the synchrotron radiation.
Okay, the star emission is first not synchrotron emission, that's a nuclear emission. As you rightly said, the star emission is mostly from a isotropic emission. Well, your question is right. The point is okay, so we have other galaxies, pulsars, many other places where the synchrotron emission is there. And you rightly said the synchrotron emission is not an isotropic emission, it's a pointed emission. It's something like electron running with a torch in its hand. Okay, fine. So there are different cases. If your magnetic field lines, they are aligned, they are very uniform or something, of course, then you will not going to receive the signal always. What you see is whenever the electron is moving towards you, you see a flash and that goes off. But in most of the astrophysical cases, you have this large scale magnetic field which is aligned, as well as there is something called as tangled magnetic field. What do you mean by tangled magnetic field is, you will learn it in the higher classes, and in astrophysical scenario, the matter exists in the form of plasma. And the plasma has a habit of freezing the magnetic field. And the magnetic field, since the plasma it doesn't freeze, it keeps whirling around the magnetic field lines randomly. So eventually, if you see it in a plasma, most of the times the magnetic field there will be a random component of magnetic field. So then you are having a race course where the electrons are running around. Now you pick up all the race courses in the world and combine them. And if everyone runs, you will always find someone is running towards you. Am I right? So that's what happens. When the magnetic field gets tangled, there will be always a radiation which is coming towards us because some electron is moving in my direction. That's how it can become
So why there is twinkling of stars? Twinkle. Sometimes we don't see it, and sometimes we see it. And then why it twinkles?
We don't see twinkle because of the pollution. There are two types of pollution: atmospheric pollution as well as light pollution. We start loving the night sky, rather we try to put up the floodlight and like to see the earth again and again. So night is given us for us to admire the heavenly bodies, but we don't want to admire it. We light our earth so bright, so the night sky becomes dull.
You have touched upon the atmospheric sciences to planetary interiors to synchrotrons and charged particles and whatnot.
So now Jyoti Singh has a question. It seems apparently she's having a problem with her mic. She is asking a question on synchrotron. Like if synchrotron is so powerful, can it be used to smash or blast the extraterrestrial rocks which are approaching the Earth?
Interesting question. But the power, yeah.
Okay. So it is so powerful, but it is not that powerful enough to blast even a meteorite. Okay, so normally what happens when the stones come, most of the times the atmosphere provides us a shield. Whereas the stones due to the friction, the stones burn off. Well, there are occasions when the stones, we can estimate, because from the mass of the stone, from the velocity, you can estimate whether it will able to reach the earth or it will die before reaching the earth. If it dies, most of the cases it dies before reaching the earth. There are certain occasions when the stones try to reach the surface of the earth, and even if the stone is of the size of a tennis ball, it's going to create a huge shock wave, which is going to cause a destruction. And most of the times it will fall on the sea also. That's why we say, because the majority of the Earth's surface is covered by sea. We all know it. So only under the cases when some stones survive to enter, reach the Earth, and if they identify the stone can hit some living area, then what they do is they try to send the explosives and blast the stone. So once it becomes pieces, then it goes off. And of course, we can't, synchrotron radiation is not that powerful enough to do this job.
So this is a classic example of how young minds connect various concepts, and it was answered very nicely by Dr. Sundar. Now Mr. Shreyas Karanjikar, you can unmute and ask your question.
Hello, sir. Sir,
Yeah.
I want to ask what will be the effect of satellite constellation technologies on future of the astronomy? So it's very hot topic right now. That's why I want to ask you. So what do you think? Like SpaceX like companies and also Amazon like companies are thinking of building 40,000 plus satellites constellation. So
Yeah,
what do you think about?
yeah, this topics eventually become even controversial. So there are a lot of emotions and everything attached to it. I would say Earth is still a place where we can live happily, provided we understand how fragile it is. Of course, as an exploration to space, to show the knowledge of to explore more knowledge from the universe and everything, of course we should go for space exploration and further. Now if you speak about this is a personal view, of course this can be different for different people. So if you wanted to build a space station or go to some space colony somewhere else, it is something you are trying to recreate a situation which is what you are enjoying on Earth. I can say nature is not that easy, which can be recreated in a short span of time. So whatever it happened, it's going to take many lifetime to be for us to achieve it. But yes, I say it is not. I'm not telling it is not achievable. Once upon a time, the human never thought they can reach a moon. When Apollo landed, when he took the Earth rise from the moon, if I show that picture to people some 1,000 years back, no one would believe it. So humans always do something which can never be believed. So of course, with that, the humans will be able to explore the space and make colonies. But of course, that won't happen in the near future. It will take different lifetimes.
Correct example of curiosity-driven research. So we are also celebrating the Mars rover.
Yeah.
In this direction.
Yeah, exactly.
So next question.
Yeah, Mr. Vansh Jain, kindly unmute and ask your question. Mr. Vansh Jain.
Hello, good afternoon, sir.
Good afternoon.
Sir, my question is, what actions have VRC taken as an institution to curb the effect of global warming in the country as well as in on the world? Because it's the biggest concern.
Maybe we take this question to the next panel.
Yeah.
Because this relates more to the to the study of various molecules, atmospherically important molecules, which can be used as a replacement for the ozone depleting things. Any more questions or?
Sunidhi Sri. Ms. Sunidhi Sri, unmute and ask your question.
Good afternoon, sir.
Yeah.
I would like to ask that how advanced is Growth India telescope?
How is? Can you please repeat?
How advanced is Growth India telescope?
Growth India telescope at Ladakh, actually it is a robotic telescope and it is used to study the transients. Transients are the the sources in the sky which suddenly starts emitting. I mean, normally it is absolutely quiet, it does not give any emission of radiation, or even if it gives some, emits some radiation, it is so feeble that we can't detect. But suddenly it flares up and becomes very bright. So now you don't know when such kind of flaring will take place. So that's why this kind of uh, they are robotic telescopes and they get triggered from such kind of emissions, and the moment they get triggered it automatically aligns itself in that direction and starts observing the source. I mean, if it is the human intervention and all other things were required, then it could have been delayed. So that's why these robotic telescopes are used there. And this telescope is a part of the program which is carried out by Caltech, USA. The similar telescopes are used there also, and they study these transients. So that is all about this telescope.
Ms. Gargi, you can unmute and ask your question. Ms. Gargi, Ajay.
Good afternoon, sir. Sir,
Yeah,
I
good
wanted
afternoon.
to ask, the gamma rays and X-rays which come from space and they can capture them and then study them. Can the rays be using synchrotron radiation be able to interact with those coming from space?
No, couldn't get the question correctly.
Can you repeat the question, Ms. Gargi?
Come close to the mic and repeat the question.
Yes, sir. So, like we are able to study the rays coming from the universe, the cosmic rays, can the rays produced by humans, the synchrotron radiations, the X-rays and all, can they be used to interact with the cosmic rays?
Something I could get
Interaction is
can
possible between us and the cosmic rays using synchrotron radiations?
Are you asking that whether the cosmic rays can be studied using synchrotron radiation?
Yeah, sir, kind of.
Yes, indeed. See, there are two ways it can be studied. First is the cosmic accelerators, where these cosmic rays are produced. There, uh, of course, this magnetic field will be there because magnetic field is omnipresent in the cosmos. So in such magnetic fields, those energetic particles can emit synchrotron radiation, and we can detect such synchrotron radiation on the Earth. That is one way. And there is another way. Recently, there is a project where this project name of the project is LOFAR, where this cosmic ray air showers, they are emitting the radio waves in that air shower through synchrotron process, and such radiation is detected by these LOFAR telescopes, antennas. So using that radio emission in the air shower, which are initiated by cosmic rays, one can definitely study the properties of cosmic rays.
Thank you. Do we have any other question on?
There is one question on chat because by one Dappili Manasvi Reddy, her mic is not working. She wants to know why are stars not visible when there are street lights on?
Of course, you put a serial bulb in front of your floodlight, so you won't see the serial bulb, right? So
That's
always
it.
when you're lighting your home in a Diwali or any festival, you put a serial light in front of the window. Now, if you think of there is a very bright sodium vapor lamp just sitting on your window, so of course you aren't able to see, you are not able to enjoy the lights, right? So what you expect is to enjoy your serial bulbs. You need a dark. Okay, and if I keep increasing, or simple explanation, why don't you see stars in your daytime? It's because sun is so bright. That's the question. So when the moment you try to pollute your atmosphere with more and more bright lights, naturally the feeble starlights become dim and you're not able to see it out.
So she has correctly found out touched the problems of typical astronomers.
Yeah.
All the astronomers actually face this problem while observing in the night sky.
We search for darkness.
Yeah, they search for darkness.
That's why we run to jungles and hill stations where no humans are around.
Correct. Next.
So if you had like keenly observed yesterday's talk by Dr. Sundar, there was a nice what you can say animation where the sun sets and he said the astronomer's life starts.
Correct.
Right? So this is the answer for that. And now next question by Posture. What is her name? Srishti Posture. Srishti, you can ask your question. Srishti Posture. Okay. Next question. Srishti, you can ask your question. You can unmute your mic and ask your question. Okay. If there are no
Can you
further questions.
Yeah, go ahead, Srishti.
Yeah, Srishti, please. Go ahead.
Sir, can you tell us about little bit about dark matter and dark energy in
I was
space?
hoping this question would. Why this question didn't come out until yet? Yeah, please.
See, the first is that dark matter. Now, this dark matter is that part of matter in the universe, of course, which is dark. Now, what do we mean by dark? Actually, this matter, so far what we know, does not participate in any kind of interaction, particularly the electromagnetic interaction, so that we can see any radiation emission from such matter and detect them. It participates only in gravitational interaction, and the first it was detected when astrophysicists started finding out the rotation, something called the rotation curve of the galaxy. What is that? If you go away from the center of some galaxy and at different distances from the center you determine the velocity of the matter which is present there, you will see that this velocity does not decrease with the distance which it is supposed to be. Instead of that, it remains flat. It remains constant at some value. Now, you can explain that if and only if you consider some amount of matter deposited in the galaxy which is not visible to us. And that matter is known as the dark matter. Now, we really don't know what is the origin of that dark matter. And people are trying in different ways, particularly through radiation. There are many theories which scientists have given, and using those theories, they are trying to predict what kind of radiation it can give. So, astronomers are trying to detect that using different telescopes. As far as the dark energy is concerned, see, there are recent observations of distant supernovae. Okay? The supernovae, there are two types of supernovae. There is one type called the type 1 supernovae. They are very good candidates to study the cosmological evolution. So, what astronomers do, they search for such type 1 supernovae, and then they measure their luminosity and measure their distance, and from that they try to find how they are distributed over different distances. So it is essentially found from such observation, the observational results can be explained if we consider that the universe is expanding, and it is not just expanding in a uniform manner, it is expanding with some acceleration. Now, the expansion of the universe was a known thing to the astronomers from around 1929 or so, when the astrophysicist Hubble, he first concluded from his observations that galaxies are flying apart from each other. So, and that can be explained if we consider the expansion of the universe. But that time, the idea was that the universe is expanding uniformly. But these recent observations, which led to the Nobel Prize in physics, it showed that universe is not just expanding, it is expanding with some acceleration. Now the question is that why it is accelerating? Because some extra energy is required for that. Now what is the source of that energy? We don't know. And that energy, whose origin, whose nature we don't know, is again known as the dark energy. Okay?
Okay, thank you for describing such a vast concept in few minutes. So with this, we now move on to our last session, which is the. Before that, I'd like to thank the panel on astrophysics, dedicated in this astronomical aspects of the theme of this uh, science day program. Thank you. Now I'd like to invite the panel of experts which you had been interacting yesterday and day before. And today's program is again based on the questions sent by you, and some representative questions which have been selected needs a bit of discussion in terms of fundamental concepts will be discussed here. And yeah, our panel is here, and in the meantime we would open the questions which were sent. So let me directly go to the questions. The first question is from Swatantrata Gupta from Hiralal Ramnivas Inter College. Miss Swatantrata, if you are online. No, she is not online right now. So the question is, when planets became black hole. So good interlinkage now. When planets became black hole, how the huge amount of matter get converted into too small. Example, when Earth's when Earth will be, I think she wants to ask, when Earth will become black hole, it's okay. When Earth's became black hole, its radius is only 8.89 millimeter, and its present radius is 6400 kilometer. Can you please comment on that?
Well, the first thing is that it's an interesting question. The planets will never become black hole. Okay, so you should not be worried that if you have some worry that Earth will become a black hole, it is not that.
It's not going to happen.
Earth will never become a black hole. See, it is the stars which go into a black hole after their at the end of their life cycle, and that too the very massive stars. The one important thing, difference between the star and the planet is that stars are self-gravitating objects. Means its own gravity is balanced by its internal pressure, which is due to the radiation and all. So such kind of system is called a self-gravitating system, whereas Earth is not a self-gravitating system. Earth is already did as far as its evolution is concerned, and it is held by its crystalline structure of its core and all. So it will remain like this. It will never be a black hole.
So the next question is.
But I just want to
Okay.
say one thing.
Sorry.
When a massive star goes into a black hole, that time lot of energy goes into, or rather I should say the major part of its energy during its formation goes into the neutrino. So most of the energy is carried away by the neutrino through some complicated process, and rest, and another part of the energy goes into in the ejecta of the supernova explosion. So it is always accompanied by some explosion, and this ejecta, which are formed in that explosion, they carry a lot of energy. But most of the energy goes through formation of neutrino.
Thank you. Next is, what is the importance of synchrotron in future? I think part of this was covered yesterday.
Yeah, it was already covered
Yeah,
yesterday.
already covered. So we'll go to the next question.
Okay.
Maybe I can tell.
Okay, briefly we can.
Yeah, so I would like to add something to this question. Actually, at the end of the festival of the synchrotron science and technology, this question will be there in everybody's mind. That what is the future? So far, whatever we have learned, that whatever is going on in this. So using this synchrotron, whatever applications so far we are making, and then we are learning. And so what is next? What will be in the future? So that everybody's mind that question will arise. So first, just let me tell you that the synchrotron, the beginning of the synchrotron machine, like yesterday question actually I answered how the synchrotron from cyclotron we converted to synchrotron for increasing the energy, and this energy increase of energy was driven by the search for these heavier and heavier particles, and especially particle physics studies. So all the synchrotron machines that have been built in the beginning was meant for particle physics studies, and these which has been used for studying this QGP quark gluon plasma to simulate the situation of the Big Bang just after a few seconds or minutes. So this quest will go on. So higher and heavier and larger and larger machines, synchrotron machine will be built. So this is one of the futures that will be for particle phase studies, and the synchrotron radiation that has been used, that is afterwards. And you know the for the last few days or whatever we have been learning these applications in different areas, especially in the future, especially the developing countries. Out of 100 synchrotron radiation machines, 20 machines are there in USA. The developing countries will be building more and more synchrotron radiation machines, especially focusing on this medicine. And one of the lectures you must have heard, where it has been told that protein crystallography to learn the structure, actual structure of the proteins, and knowing that, understanding the structure, one can make the medicines such a way that these use will be there, and then more machines will be used. So starting from biology, medicines, quantum meter, material science, everywhere it will be hugely used. So this is the future of this information.
Thank you. Next is Yogesh Ashok Joshi from BK Birla College. Yogesh, if you are there, the question Yogesh has put up is how day-to-day life we can use nanotechnology. So nanotechnology, this is a new question.
Okay, so I think you have, Yogesh, I think you know something about nano. Nano is nothing but say 10 to the power minus 9 nanometer. So in that length scale, the physics is basically governed by the high surface area, and this property gives some special property to some the materials, and you can have new materials based on the nanostructure property, and it has many applications starting from your food to maybe any nanoelectronics, nanomedicine. It covers almost all spheres of life. I will give one example. Say take a textile. You must have seen the water on a lotus leaf. It almost floats. And there, taking this example from the nature, nowadays people have invented some kind of special fabric where water will not touch. And in this regard, I will say, because we also have responsibility for the society, and Baba Atomic Research Center recently, they have invented some kind of bulletproof jacket taking the advantage of these nanostructures, which is known as Baba covers. So this is very useful for the lightweight bulletproof jacket. So these are the typical examples of nanotechnology in nature. And apart from that, of course, you have in food, you use soap in the daily life. So there everywhere you see there is a presence of these nanostructures, and if you can control this nanostructure, you can have very nice materials, improved material properties, and here synchrotron plays an important role. You can characterize these nanostructures with this synchrotron.
Okay, thank you. What is synchrotron science? What is its history and how it is useful for scientists? So this is what we have been discussing on all 3 days. So we'll skip this question. Next question is by Yusuf Ayub Khan, Our Lady of Good Counsel House High School. Yusuf, if you are there, you can unmute yourself and ask your question. The question which Yusuf has posed is, what is synchrotron science and what are its effects on the living world?
Dr. Jha,
Dr. Jha? Yes, we are trying to connect. Okay, so Dr. Jha has already answered this question yesterday also. So we'll move to the
I
next
think it's
question.
similar question. Yeah, you can move.
Yeah,
to
yeah,
next.
okay, yeah, fine. The next question is by Vansh Hansmukh Jain, Our Lady of Good Counsel High School. As we know that by the way, Vansh is there. Can he ask his question?
Yes, sir.
Yeah, please.
So, as we know that the upcoming generation are losing interest in the field of research and more attracted towards glamour. What measures are sorry, sir.
Yes, Vansh.
As we know that the upcoming generation are losing interest in the field of research and more attracted towards glamour, what measures are taken by VRCs to develop interest in the field of research?
Right. You see, the coming generations now, in last 20 years, there is such an expansion in encouragement of pure science in our country that many people in your generation and these coming generations are actually also choosing to do research in not just like physics, chemistry, biology, mathematics, but there are areas which are at the intersection of many of these fields. So there are new fields which have emerged. So I first of all say that I am a little bit of in disagreement with the fact that people are not losing interest, but of course they are enamored by the glamour. The reason for glamour is natural because something looks bright, you always look towards that. But glamour in other areas and glamour in science. Glamour in science is identified by doing very good research, very nice applications, building new technology, doing great experiments, searching for truth, and trying to do something very beautiful. That is what is our idea of glamour. At BRC or any other institution, the interest to the society is created by the fact that we try to do very important problems, address important questions of social relevance and fundamental importance, and that's our idea of glamour. And I think there is a lot of evidence. There are movies made on what we do. There are things which are publicly available. So I think BRC will keep doing everything in its powers to do great things in research and become a focus of attention. But we are not trying to become glamorous. That's not a great idea. We try to do important things, other things follow us.
Yeah, thank you. Next question is by Dhruv Kataria from Venkateshwara Global School. Dhruv Kataria, the question is, how is synchrotron helpful in real life or in scientific advancement? Two different questions, both of them answered yesterday. So we move forward to the next question by Janki Kothalkar from AECS2. Janki, you are there?
Sir, what are the different types of synchrotrons used?
Okay, I'll answer to these questions. Synchrotrons are actually, if you are just talking about the machines, then synchrotrons, as like yesterday I have told again, same thing that has been next to cyclotron, and this depending upon the particles that accelerates. It can be like electron synchrotron, proton synchrotron, or even heavier waves. So, for example, LHC, it can accelerate even heavier beams laid starting from proton. And so these are different types of synchrotrons. But unlike electron synchrotrons, the heavier synchrotrons, the synchrotrons that accelerate the heavier beams, they do not uh, produce the synchrotron radiations, synchrotron lights, the way it does for electrons, because it is difficult for the heavier particles to to acquire the velocity which is almost equal to that of light. And depending upon the energy, so the synchrotron, again, suppose you consider the electron synchrotron, depending upon the energy of those electrons, the synchrotron radiations are of different ranges in the sense different energies or different wavelengths or different frequencies. For example, in our cat indoor, there are two, Indus 1 and Indus 2 stage. So the first stage is only 450 MeV that generates the X-ray in the range of ultraviolet range. And for Indus 2, because their energy is higher, that 2.5 to 2.5 GeV, the energy range is the synchrotron radiation that produce in the range of X-rays. So depending upon energies, there are different synchrotrons, synchrotron radiations for the electron machines, and depending upon different particles, they are named different synchrotrons, proton synchrotrons, or even heavier synchrotrons. So I think that gives some idea about types of synchrotrons.
Thank you, Dr. Santra. Next question is Dikpal Yadav from Hiralal Ramnivas Inter College. The question which Dikpal has posed is, what is golden ratio and why it is important in the science?
Okay, I will try to answer these questions very briefly. See, it's interesting questions, of course. You know, you play with the numbers. So, like you start from 0, then you go 1. You add these two numbers, you get 1. And then 1, and then next one, you get 2. So, like this, you add the consecutive numbers, and then you get a series that in mathematics something is called, you don't have to remember, there is Fibonacci series. Now, the important point is if you divide this consecutive these numbers from this series, you get approach to a number which is 1.618. This number is very important. It is like something like today's it has become something like universal constant. And this number, if you see, it is related to many beauty in the whether it is music, whether it is aesthetics, many things. Like you see the Leonardo da Vinci's Mona Lisa painting. There also this concept is used. Apart from all these things, nature you see. But what is the science? Where do you get this? Is that in 2011 the Nobel Prize was given for the quasi crystal, some crystal which has a special property, and it has related to the pentagonal symmetry. And if you see for a pentagon, the ratio of one of the diagonal and two, that is exactly that one. That is an irrational number, of course, but it is 1.618, something like that. And this Nobel Prize was given for this. And so here, this concept of this is very important. Another important thing I will just mention here. If you know this synchrotron meeting, this electron and protons, these charged particles are very important. So they also have the magnetic moment. And if you get some ratio of their magnetic moment and there are some angular momentum, people have recently found that there is a nice correlation with this golden ratio, which is 1.618. If you see this number 1.618, and it will be nothing but you write this number as a phi, you can write phi is equal to 1 plus 1 by phi. You will be able to see this. And another important thing in science, if you see the DNA, the helix total length and the width, it is 34 nanometer, 34 Armstrong by 21 Armstrong. If you take this ratio, it is also 1.61. It is very nice. So like this, in many ways, starting from the DNA to the universe, you can correlate with this number to a spiral, and these galaxies and all what has been told, it is related to this. So nowadays it is believed that this number, which is golden ratio, is related to some kind of universal constant, and it has a very nice implications in science as well as aesthetics, everything.
Thank you, Dr. Sen. So we take one last question by Namita Gandhale from SRP Junior College. Namita, can you please unmute yourself, open your video and ask your question? Yes, Namita. We are able to see that you are there, but okay, I'll ask the question on her behalf. What is synchrotron XRD? Dr. Jha, Dr. Jha, are you able to hear us?
Yes.
Yeah. X-ray diffraction is the question.
Yeah, basically, hello.
Yes, we can see you and hear you. Yes.
So basically, synchrotron XRD, unlike the laboratory XRD, where we have only single wavelength, for example, we use copper alpha. Here in synchrotron, since it is tunable, we can choose any wavelength precisely. There is no need of any filter, like we put some copper beta filter. So we can tune the wavelength anywhere, and there are advanced versions like there is some echo actually.
No, we are able to hear you, sir.
Okay. So that is the basic difference. We have a range of wavelength, so we can do more precisely, especially when there are some impurities phase which is not seen by laboratory X-ray source. We can see here synchrotron XRD because it is a brilliant, it is very high brilliance. Okay. So very minute changes or in the structure or minute impurity phase can be detected. So the brilliance and the continuum ability is the important factor.
Okay. Thank you very much, sir. Thank you. So with this, we would like to conclude this session, and Thank you to all the expert panelists here for joining and answering all the queries of the students. We now move on to the concluding session of this whole 3 days program, and the students have sat down patiently and heard various speakers, various kinds of panel discussions, movies, and all those things were there. For the concluding session, we would like to first invite Associate Director of Physics Group of Bhabha Atomic Research Center to felicitate the speakers who are physically present here at the moment. At least we can do that because the speakers have done a tremendous job explaining the complex phenomena in a short span. May I invite Dr. Himanshu Poswal to please come up on the stage and request Associate Director of Physics Group to kindly felicitate Dr. Poswal. Dr. Ajay Mishra from High Pressure Physics Division of BARC. Dr. Sundar Sahayanathan from Astrophysics Division of Bhabha Atomic Research Center. And Dr. Subir Bhattacharya. May I now invite May I now invite Dr. Yusuf to deliver the concluding remarks. So students, thank you very much for patiently listening to us. We would be concluding the session with the concluding remarks by Associate Director of Physics Group, and in which a summary of what all happened during the last 3 days would be there. Please bear with us for a few seconds. Yes, sir.
Thank you, Dr. Himal Bhatt, for giving me this opportunity again. And before I summarize and give my views in this concluding session, would like to go through this some of the pleasant memories which we have been having over these 3 days. And as you see here, you see the group photograph with all dignitaries, and you can see the presence of my other colleagues also as well. See, this is Director BRC, Dr. A.K. Mahanti. This is the Chairman of Atomic Energy Commission. Sorry. This is the Chairman of Atomic Energy Commission of India, Dr. K.N. Vyas. This is our chief guest, Dr. R. Chidambaram. Now this is where I am giving the introductory remarks. I'll come back to a few points what I said on the other day. And this is what you see. Director BSc is addressing the gathering by delivering the welcome address. This is where Dr. K.N. Vyas, Chairman, Atomic Energy Commission of India, delivering the inaugural address. You know, it always gives a very refreshing memory and refreshing satisfaction when you go through your whole album. So this is what this album has been generated over these 3 days. And of course, you will not be disappointed. Some of you are also featured in this album. You will come to that. So this is where the dignitaries are being felicitated. You see one after the other. You see one after the other. This is where I was felicitated by my colleague, Dr. Alka Garg. She is not seen in the picture. This is where the dignitaries are sitting on the dais, and I am delivering the inaugural. So I am delivering the welcome introductory remarks. And you see our auditorium, and as you can see that we only invited very limited participants from Bhabha Atomic Research Centers, and all of them are leading one particular activity in Bhabha Atomic Research Center, and enough physical distancing, social distancing has been maintained due to the pandemic situation. But it was good that we could organize this event after this last 1 year, the so-called horrible experience, and we are slowly coming out of it. And of course, the students, you all join online, and I must thank all of you for that. Though you could not be invited to visit Bhabha Atomic Research Center physically, I'll again touch upon this part in my next address. And this is what you see, Dr. R. Chidambaram. He is delivering the keynote address. And his title of his talk, Science Then and Science Now. This is what he started with this picture of Sir C.V. Raman. This is what you see another part of this, our auditorium, where this, my very hardworking, enthusiastic colleagues, they're taking care of these live videos, what you all experience these 3 days. So you know, for everything behind some people is working. That is what you have to know. Without hard work, nothing is possible. And that is what has been rendered by my colleagues from physics group of Bhabha Atomic Research Center. Then, of course, food is always integral part of any event, though this is, as I said, in this situation, we had a limited gathering, and this is outside our auditorium, this cafeteria area, where you see all dignitaries and invitees, maintaining enough social distance. They're having, enjoying cup of coffee and with high tea with snacks. You see another view. I am not out of that. Some views you can see. You see my colleagues, how they are taking care of the dignitaries with personal touch. This is Dr. Himal Bhatt. He has been managing this dais for last 3 days. And this is our very first technical speaker, Professor D.D. Sharma from Indian Institute of Science, Bengaluru. And he spoke on this aspect, as you have already experienced that. This is what I'd like to tell you something, because other day I was having a meeting with him, another meeting that was, I think, DST meeting, Department of Science and Technology meeting, if I remember. So there he said, this background, what you see, it is not his office. Actually, he is at home, but he has given this background as if he is in the office. So this is what is the technology. And every situation, the last 1 year situation also taught us many new things. And as you see today, we could arrange this program where with the targeting 1,000 students, we could do online. We learned all these techniques. We learned the benefits of technology and science. This is the other speaker, Professor Dipankar Bhattacharya from Ayuka, Pune. You all have, this is my colleague. He is talking, he is delivering his talk. The Himanshu, Dr. Himanshu Paswal. Then this is Dr. Tapas Ganguly from Rajaramana Center for Advanced Technology, Indore, where the synchrotron is physically located, the Indus 1 and Indus 2. He belongs to RRCAT. This is again my colleague from Physics Group of Hava Atom Research Center, Dr. Sundar Sahanathan. He is delivering his talk. He spoke both the days. And you see some few pictures we have captured, the young minds, how they are so much enthusiastic. I saw this boy, he asked, I think, more than 2 questions, so he could place himself. There's so much excitement you see. Of course, there are many more photographs you will see if you see the YouTube, all are recorded. So you can go through YouTube and see your own photographs, because these are all live. So you are always recorded, you will be there. But here some few representative pictures have been captured. See the expert panel, they clear your doubts. See the another view graph of the expert panel meeting. And with this, now, is you'd like to announce?
See, the following are the winners of the National Science Day Quiz Program. The first prize winner is Mr. Pritish S. Maharshi. Pritish S. from Maharshi Vidya Mandir Senior Secondary School. Second prize is Mr. Subramanyam Garimella. He is from the Doon University. The third prize is shared by 2 persons. One is Mr. Shreyas Karanjikar of BK Birla College, Kalyan. Shreyas was asking a couple of questions in all the sessions. And the other one is, the one who is sharing the third prize is Asmita Anand from Atomic Energy Central School, number 1.
So all these, first of all, congratulations to all the prize winners, and you will be getting certificate from us. We'll send a certificate to each of you, and along with some cash prize. Here the number 3, what you see A and B, this is what in physics you have come across called degeneracy. They are at the same level. So here the degeneracy, we could not lift it. Probably you can apply magnetic field or electric field, some perturbation or pressure, what works to lift the degeneracy. But in our case, it was impossible to lift the degeneracy because both of you answered similar, same number of questions correctly, and also your timing was also same. Means you answered, send your responses at the same time. Okay, so that's why we could not leave the degeneracy. So congratulations to all 4 winners. So you will receive your certificates from us and cash prize. So with this, let me go to the brief summary of this event for last 3 days, what you have experienced. So this is this great day, that is the 28th of February. And we have been celebrating, whole India is celebrating, BRC Bhava Atomic Research Center is celebrating. And this year, we are fortunate the physics group of Bhava Atomic Research Center was given the responsibility to celebrate this great occasion. So the celebration of this kind, it always fulfills several purposes. One fold is, of course, give the message of the great discovery, what the discovery was, and another thing, of course, what went behind the discovery. As you can remember, some of you, that in my introductory remarks, I gave some highlights. We recall some historical facts that only tells us that what goes behind to achieve this kind of unbelievable target and to win the best prize, best recognition in science, in physics, what Professor C.V. Raman, Sir C.V. Raman could do, achieve it in 1930 for his work in 1928, and precisely on 28th of February, official date for that Raman effect discovery. Of course, that was the origin of this National Science Day celebration, but the larger purpose is that science does not stop there. The great discovery opens up a new area, and scientists and engineers, they put their mind together, they put their best effort to take these ideas forward. And as I mentioned on the very first day again, that the light source which was used by Professor C.V. Raman and his students, to start with, it was in fact sunlight by using focusing action by focal lenses. But later on, they also used the mercury vapor lamp, but that was not that adequate. Of course, adequate enough. With the innovation and great deep knowledge in physics and dedication, they could make sense of it and they could start a new branch of physics. But so that limitation, through the journey of science and technology, through the advancement of science and technology, this limitation we have overcome, and that is what you have witnessed, nothing but the synchrotron light source. Of course, this has given much more. This has given not only the high brightness, the high brilliance, it also has given the tunability, the effectively very, very large spectrum of the electromagnetic radiation. So it is not only the visible light, but on the both sides of the visible light with respect to wavelength or frequency. You have also seen how the synchrotron radiation can come from universe. And also you have heard that how the Department of Atomic Energy in Leh Hanley, we are fully prepared to capture that part of science as well by so-called the MES telescope, the gamma ray telescope. So this is what is the beauty of science and technology. A great discoverer, a great scientist gives some idea, and then it takes us to a higher and higher dimension with a great effort from this. And over the last 3 days, you have heard many talks covering these aspects. What are the basics of the synchrotron radiation? What is synchrotron radiation? What is physics behind that? What is the technology behind that? How to get synchrotron radiation? How to manipulate it? How to enhance its properties? How to use synchrotron radiation for doing science, for understanding the nature, for solving problems, the unknown problems, getting answers to unknown questions. And finally, all these things lead to the development of mankind. That is what is the ultimate purpose. Besides the intellectual satisfactions, we have also gone through the special sessions where the question answers, the quiz, the panel discussion, all are very, very important because you could interact, these young minds could interact with the learned scientists from Bhabha Atomic Research Center and from other organizations. Even after each and every lecture also, there is enough time was given to have scientific discussions. So that was very important, and there you have interacted with each and every speaker. Of course, in this limited time, it is not possible for all the to accommodate all the questions from large number of participants, but we have taken care to accommodate as much as possible within the given time domain of this program. But I must tell you that the movie or the film which we made, that was a box office hit. You all will agree with me. And I am making this statement based on your questions and the level of questions and level of understanding. So unless and until the film makes the hit, box office hit, this kind of questions cannot come. And this is a movie which you will feel like seeing again and again, and that I can see from the interest to attend this program all through 3 days. Some of the faces I can see again and again. Some of the names are coming up. They're asking questions almost every day. So this is a very good spirit, and for this program to happen, to bring in front of you this program for these 3 days, my colleagues from the Bhabha Atomic Research Center Physics Group, they have worked really hard. They have given enough thoughts. They have given enough time, enough energy to come to this stage, and we have experienced the fruits of that. Of course, the purpose is that to ignite the young minds, because you are the future of this country. I'm sure many of you had dreams over last nights that you are also rotating or you are also getting accelerated and almost close to the velocity of light. And probably your dream, you wake up when you realize that you are going to possibly cross the velocity of light and that is not possible, and that then you wake up. So this kind of dream is always required. That gives the excitement in life, and unless and until the dream of hope is that is what gives you the acceleration in your life. Whether you are a student or you are a scientist, you are working in a lab, or whatever be your profession. So dream of hope always gets you accelerated in doing what you want to do. And the dream of success is equally important, because unless and until you have dreams of success, you will not be probably achieving that. The success, in order to be a successful person in a given domain, in order to fulfill your objectives, in order to deliver your targets, in order to go beyond the threshold limit and show the world in your own domain, you must dream of success. So this is the program. I'm sure that many of you have come to the stage, and if that is so, that is the success of our effort over last more than 1 month. And this year, due to this pandemic situation, we had to organize this meeting online, and that prevented you to visit physically this great organization founded by Homi Jahangir Bhabha, this Bhabha Atomic Research Center. But of course, we have tried our best even to take you through the virtual tours of various facilities of Bhabha Atomic Research Center. But nevertheless, if some of you are still very much interested, through your principal, you can approach us after the pandemic situation is over. We'll try our best to arrange your visits and to show the facilities which the scientists and engineers have built, and you will experience in yourself. So with this, I convey my best wishes to all of you for your future, and with this I thank all of you and Jai Hind.
Thank you, Dr. Yusuf, for this nice concluding. These are nice concluding words, and also guiding us through the course of organizing this event. I now request Shri Sampath Kumarji from Bhabha Atomic Research Center to deliver the vote of thanks.
Good afternoon, Dr. S.M. Yusuf, Associate Director, Physics Group, colleagues, and enthusiastic students who have been participating online during this National Science Day celebrations 2021. Gratitude is not only the greatest of the virtues, but it is the parent of all the virtues. So it's my pleasant duty to thank all those who have been a crucial part of this great success story that is NSD 2021. First and foremost, our sincere thanks to Dr. R. Chidambaram, former Principal Scientific Advisor, former Chairman Atomic Energy Commission, currently Homi Bhabha Chair Professor, above all, the father figure of physics fraternity in India, for gracing the NSD 2021 in spite of a series of meetings scheduled for the day. Sir, it is our great privilege to have your august presence, valuable guidance, captivating keynote address, and the best of your blessings. Thank you very much, sir. We heartily thank Dr. K. N. Vyas, Secretary, DAE, and Chairman Atomic Energy Commission for participation in NSD 2021 amidst his tight schedule. We thank him for releasing the booklet on NSD 2021, inaugurating the National Science Day 2021 proceedings, and setting the tone for the enthusiastic interaction with the student community. Thank you very much, sir. A million thanks to Dr. A.K. Mohanty, Director BRC, for entrusting the responsibility of conducting the National Science Day 2021 to Physics Group, directing various teams of BARC, technical as well as administrative, to be of support to the organizing team as and when required, periodically monitoring the progress by way of personal interaction, scheduling his outstation appointments to enable participation in the function, delivering a motivating speech, and instilling responsibility in your minds, these young students' minds, by emphasizing on making our country Atmanirbhar Bharat. Thank you, sir. We thank Controller BRC for according the necessary approvals for the usage of this DAE Convention Center and scrutinizing closely our videos which are made and granting permission for screening the videos which are made specially for NSD 2021 and also participating in the NSD 2021 celebrations. Thank you, sir. Our sincere thanks to the members of the Trombay Council for according the approval for NSG 2021 celebrations on the virtual meet platform and providing necessary funds, providing guidance, and wholeheartedly participating in the NSG 2021 celebrations. We thank Sri Jakotia, IFA, BARC, without whose direct involvement to speed up the process of placing order for getting the videos made, making of these videos, wonderful videos, which received wholehearted appreciation from the dignitaries, would not have been possible. A very big thanks to you, sir. Our hearty thanks to Dr. S.M. Yusuf, Associate Director, Physics Group, for the meticulous planning of every single task in detail amidst his extremely busy schedule, forming compact teams with focused goals and guiding them constantly, empowering the teams with freedom as required to implement the assigned tasks, monitor the progress closely, and motivate the teams to celebrate NSG 2021 in the best way as it happened in the past 3 days. Sir, your team will always cherish this wonderful experience of grooming under your wings. Thank you so much, sir. We express our sincere gratitude to the Vice Chancellor, Homi Bhabha National Institute, for supporting the conduct of NSG 2021 by providing the Cisco WebEx platform and the consistent and reliable support of Mr. Anurag Sharma, which made it possible to conduct the event in a smooth manner. Since the past 3 or 4 weeks, Physics Group and Computer Division functioned with so much synergy to see this program through with utmost perfection. We thank Sri P.P. Marathe, Director, E&I Group, and Sri Rajesh Kalmadi, Head Computer Division, for guiding their team to the level of perfection that we all witnessed in the past 3 days. We thank Mr. G.G. Joseph, the key brain behind the before schedule implementation and glitch-free operation of the high-speed network and the VC systems at the DAE Convention Center, and motivation of his brilliant team comprising of Mr. Akshat, the expert who brought in the perfection through his meticulous planning and thorough involvement with able and ever-ready technical support from Mr. Anil Jadhav and Mr. V. Arun Kumar, apart from the seamless YouTube live streaming by Mr. Surya Pratap operating from the supercomputing facility building. We heartily thank the computer division team for their unstinted support, which was extremely crucial for the successful conduct of NSG 2021. Again, the two aces who held the hardware and software forts in the field, Akshat and Anurag, do deserve a very special mention. Our sincere thanks to Sri Debashish Das, Director RRCAT, for according the approval to a team comprising of Dr. T. Puntambekar and Sri Sanjay Chokse, who readily provided us with videos on intersynchrotron radiation facility and a lot of relevant information pertaining to synchrotron science and technology that helped us so much in the making of these wonderful videos. We owe Dr. R.K. Vatsa, Head Public Awareness Division DAE, a big and hearty thanks for taking personal lead in providing us with the videos highlighting BARC and DAE facilities for streaming on Cisco WebEx and YouTube platforms with appropriate permissions from the competent authority. All this done on a request with a very short notice. Thank you very much, sir, for the timely help. We thank Sri Uday Avasare, ACE Information Technology of Heavy Water Board, for providing us a nicely compiled video on heavy water for screening during the National Science Day celebrations 2021. We thank the invited speakers, Dr. D.D. Sharma, IISc Bengaluru, Dr. Dipankar Bhattacharya, IUCA Pune, Dr. Himanshu Poswal, HPSRPD BRC, Dr. Tapas Ganguly, RRCAT, Indore, Dr. Sundar Sahayanathan, APSD BRC, Dr. Ajay Mishra, HP and SRPD BRC, Dr. S.N. Jha, BDAS Physics Group, and who is currently at RRCAT Indore, and Dr. Subir Bhattacharya, APSD BRC, for providing highly informative and inspiring talks to inculcate interest among students to pursue further learning about the central theme of NSD 2021, namely synchrotron science and technology. Our thanks to the members of the discussion panel, Dr. T. Shakuntala, Dr. S. N. Jha, Dr. Sudhir Jain, Dr. Satyaranjan Santra, Dr. Debashish Sen, Dr. Kuldeep Yadav, Dr. Subir Bhattacharya, and Dr. Nilay Bhatt, who dispelled various doubts that rose in the young minds, leading to their clear understanding of the concepts. Thank you, sirs. Our sincere thanks to SIRD BARC for publicizing NSD 2021 on BARC website. Our thanks to Chairman's Office, Director's Office, Controller's Office, and Office of Dr. R. Chidambaram, Homi Baba Chair Professor, Sri Dashrath Dogra, PRO BRC and his team, administrative staff from various divisions in Physics Group and Group Office of Physics Group, Sri Sadanand Malar, AO3 TSH and his team, Sri Ravi Bilgi, Senior PS to the Vice Chancellor, HBNI and his team, Accounts Division BRC, Transport Section and Security Section of BRC, Sri Narendra Kumar, Head IT Division DCSEM and his team for providing us with all the required internet infrastructure at the DAECC auditorium, Sri S.K. Tiwari and his team for air conditioning facility at the auditorium, audiovisual team guided by Sri Anil Pundalik, Head Electrical Division of DCSEM and his team, and implemented ably by Sri Sachin Vanzole, who was all the time with us. We had taken so many trials and all that, and his highly cooperative team, all the DAE Convention Center staff, Sri Gurukesh Kopatkar, who made this excellent video. He was all the time with us and he was listening patiently to our inputs, and he is the one who made this excellent video. Sri Gurukesh Kopatkar and his team from Mrs. Guru's Academy for making two excellent videos on SR Science and Technology. Mrs. Anusat for providing the backup network facility. Mr. Ali for efficient video coverage of this event. Sunil Decorators for the beautiful floral arrangements in particular. Sri Arun Shetty and his catering team for providing tasty and hygienic food served, strictly following pandemic situation related guidelines. And Sai Services housekeeping team who doubled up in helping us in logistical arrangements also. Last but not the least, Raman, I wanted to be shown. List of volunteers. Yeah. Last but not the least, the organizing team, which has done everything, as our associate director was telling. It is a wonderful team that has been coined meticulously by our associate director and guided by him. So as I was talking, this is a team. There are various committees. It is formed as a team actually, and this is the list of members of that team. You can see. So this is the team which was involved in conducting this National Science Day 2021. I hope all names have been included in this. If some names have been missed, like kindly understand that it is maybe a slip and it's not intentional. So this is the organizing team of the NSD 2021 who have been tirelessly putting in their efforts, be it the video committee. We will all be missing this everyday 9:30 to 11 meeting from now on, and this publication committee who have been bringing out all this booklets, banners and all that. Every committee, the coordination team has approached, they have physically visited the colleges and motivated the students to participate. So there are all these teams which have participated in the best way. And last but not the least, it is the enthusiastic students. Pan-India participation. Students from across the country have participated in this event, and they have really, students, for you, these videos, as our director was telling, we have made these videos especially for you. Lot of effort has gone into that, and you have appropriately understood and enjoyed, understood and gathered the concepts which have been brought to you through those videos, and you are asking questions. We are very happy about it. So this enthusiastic participation, as our associate group director Dr. S.M. Yusuf has promised, like you will be sent these prizes for participation and winning. Participation certificates also will be sending to you all, and for winners you will be getting winner certificate and cash prizes. And I thank Sri Himal Bhatt for comparing the event, a fantastic job that he does so naturally. Thank you, Himal. So I seek your pardon if I have unintentionally left any one of you in this vote of thanks. In order to make up for slips, if any, in the end, I thank all of those who were involved directly or indirectly in the successful conduct of NSD 2021. Thank you all. Jai Hind.
Thank you, Sampat Kumarji, but I must say that you have left a very important person. That is not good. Please, can we have a big hand for Sri Sampat Kumarji for looking after all the things very meticulously. And before we disperse, we'll all have national anthem, sing national anthem before dispersal. You can start. जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंग विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तब जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे. Thank you. Jai Hind and Jai Vigyan. We now close this session.